project itself. The project SPINTECH, supported by European Commission, called Boosting the Scientific Excellence and Innovation Capacity in Spintronics of the Institute of Electronic Engineering and Nanotechnologies of Moldova. Coordinator of this project is our Institute of Electronic Engineering and Nanotechnologies in Moldova, in collaboration with two West European partners, Twente University with Professor Alexander Golubov Group, and Stockholm University of Professor Vladimir Krasnov Group. The main goal of this European project is to increase the excellence of Institute of Electronic Engineering in Moldova through the exchange of knowledge and transfer of knowledge and experience from West European universities, from Stockholm University, technological approaches in fabrication and characterization of functional nanostructures, and Twente University, which has a long-term experience in low-temperature physics, in squid magnetometry, and what is especially important for our project, in theoretical investigation of functional nanostructures. Professor Alexander Golubov is one of the authors of the new direction in superconductivity, so-called non-conventional superconductivity triplet pairing, which is very perspective for new applications. That's why this consortium, University of Twente, University of Stockholm, and Institute of Electronic Engineering and Nanotechnologies are working together, and during this project, the period implementation of this project, it will be extension of networking. And this year, to this consortium was involved also a group from Amiens, France, Professor Lukinchuk, he is coordinator of the project in similar area. He will present his project a bit later. And the end result of the implementation of SPINTECH project is increasing of competitiveness European science and innovation area in the world map, and developing of base for new supercomputer elements base, so-called non-von Neumann architecture, brain-like activating neural network. And for this purpose, we shall develop, this is complex aim, and a lot of participants will be involved in this activity. It will be the further goal. But as I told already, the direct goal of this project is boosting of excellence of Institute of Electronic Engineering and Nanotechnology through the knowledge transfer and exchange. Our institute is has 30 years experience in developing various vacuum technologies for films and nanostructures fabrication, and we are collaborating with Germany. More than 20 years we collaborating with Augsburg, Karlsruhe, Stuttgart, with Stockholm, Sweden, with Holland, Twente, with Russia, theoretical groups from Moscow, Professor Kuprianov, Professor Leonard Tagirov, and modeling Professor Vakhrushev, and experimentalists from Moscow, Institute group of Vasily Stolярov. And now this year we collaborate with France also with Professor Lukyanchuk group, Melon project. That's why all together exchange knowledge, experience, facilities for development of novel base for supercomputer. State of the art of the project. This project, based on the theoretical and experimental results presented in the book Functional Structures and Metamaterials for Superconducting Spintronics, printed in 2018 in Springer, were chapters of Professor Golubov about theoretical investigation of functional structures, and our chapters developed about development of technological approach for fabrication of such functional structures and metamaterials. And on the base of this knowledge, which was already done, which was already summarized, we prepared this project for further development of elementary base for computers. Why it is important? Last decade, the semiconducting base elements for computer reached nearly the limit of further development, because the main problem now is not increasing of the number of transistors, single elements in chip. The most difficult problem is energy dissipation. Consumption of energy semiconducting computers increased enormous. For example, one of Google servers placed in Sweden, energy consumption approximately 10% of the whole country energy consumption. And the proper way to develop a computer with lower energy consumption will be to change the element base from semiconducting to the novel one to superconducting elements, which has no dissipation of energy, and it allows elaboration of computer with 3-4 orders lower energy consumption. It means that the future is for the development of computers lies in the new elementary superconducting elements, which we are investigating in frame of this project. In our institute, this project is carried out in the cryogenic laboratory, where, as I told, during the 30 years, we developed a lot of various vacuum technological processes for fabrication of thin films and layered structures for microelectronics. And the partners of our SPINTECH project, University of Twente, as I told, has unique facilities, squid microscope, which allows investigation with high resolution of magnetic.
One moment, there is a technical problem because your screen is not visible. Can you share your screen? Alexander Brinkman is calling. Okay. They only see part of your screen. Okay. Just a moment. We will try to arrange. Okay. Yeah. You share screen now?
You
should share screen.
You should please share your screen. Okay.
very please. We will check.
You go to Zoom.
Presentation mode first.
Yeah, that's good.
Guessing that's share screen.
It's this one.
That was the right.
Now it is good.
Yeah, now everyone will see you and your share screen. So,
But that's a picture that we did not recognize it earlier. It is now. It is okay. Yes. Okay. Okay, dear colleagues, let us continue. Our Institute of Nanotechnology Cryogenic Laboratory has a long-term experience in vacuum technologies, as I told. Twente University Professor Golubov group has experience in theoretical investigation of functional nanostructures, developing the theory of triplet pairing, of spin valve structures, calculation and prognosis of the possible application of such effects, such phenomena in superconducting elements. And more important for our projects, they have unique device, squid microscope, which allows determination of magnetic configuration of functional nanostructures, which is vital important for superconducting spin valve, as I will explain later in my presentation. In Stockholm University, Professor Vladimir Krasnov, he is in this picture in clean room. They have a very developed and expensive clean room with all facilities in clean zone. Photolithography, deposition machines, molecular beam epitaxy or magnetron sputtering of thermal evaporation, various machines and their characterization. Everything is in clean zone, and it allows us fabrication of necessary metamaterials and to construct on the base of them functional nanostructures for superconducting spintronics. And for achievement of the goals of the project, as I told, the goal is of the project is elaboration of novel elements for superconducting computer. In this project should be done three objectives. The main objectives, to enhance the research and innovation capacity of our institute through the knowledge exchange from that groups which I mentioned above. In this project, three big work packages. One of them is short-term staff exchanges. Our collaborators last year worked many months in Stockholm University, learning these technological processes of fabrication, functional nanostructures, and their characterization in low temperature equipment. The second work package responsible for the second work package is Professor Golubov, is training workshops, conferences, and summer schools. It is a very important part of the project. because it is the proper way for the knowledge transfer during the conference, especially during summer schools. The lectures which give excellent lecturers will give the new knowledge to the participants, to the scholars, and they can learn from the first hands, from the persons who elaborated these approaches. That's why this is the second summer school, and it first was organized in Kishinev last September, and the second summer school here in Twente in Zoom format. But nevertheless, all participants who registered for participation in the summer school can gain new knowledge, and more the lectures which will be presented later, they will be recorded and will be placed on the web page of our project for further study and implementation for our work. So the structure of the project is rather complex for fulfillment of all these three web packages, but implementation of all these activities should give us the possibility to elaborate at the end of the project a working prototype of superconducting elements for for Neumann architecture of computers. So now let me go to the lecture about the functional structures, smart technology approach for the fabrication, which was developed already in frame of this project on the base of knowledge which we have previously. So in collaboration with all partners who I already mentioned above. The content of my talk today will be as following. First of all, motivation of the work. Why it is important to elaborate new elements if we have already good elements semiconducting chips. Then development of novel technology for especially for detection of predicted phenomena, which was predicted theoretical groups from Moscow State University, from Twente University, from London College, and other theorists who developed the theory of non-conventional superconductivity. Then detection of triplet pairing and memory effect in superconducting spin valve, which was fabricated using this elaborated technology. And one very important part of our work is modeling of the technological processes, fabrication of nanostructures. Why it is important, I will explain a bit later. And then the conclusion and recommendations. So, motivation of the work is, as I mentioned above, development of the base for Neumann computers, artificial neural network, as alternative for existing semiconductor computers with extremely high energy consumption. And to resolve this problem, one shall move to another architecture. For example, to the artificial neural network or non-von Neumann architecture. The idea to use superconducting elements is relatively old. Even John Brenner, in his book in 1959, proposed cryotron, the element switching from normal to superconducting state using a magnetic field, Neubaum or Tantal film. But this element, it does work, but it needs a very high magnetic field, external field, comparable with the critical field of superconductor, some killer states. That's why it was just demonstrated the possibility, but for technical application it was not interesting. And that time rose the question, is it possible to control superconductivity using a weak magnetic field, which is necessary for a real application? And the answer was positive, yes, but for this purpose one shall use non-conventional superconductivity. The first superconducting memory element was proposed in 1997 by Malcolm Beasley, so-called Beasley superconducting memory element. The idea is very simple: to take superconducting film and to place it on the two ferromagnetic layers, and switching magnetization of these two layers from collinear to non-collinear. One can switch superconducting layer to normal on non-superconducting state. The idea is simple, but realization was poor, and Malcolm Beasley in Augsburg, as he was on the conference, told, yes, but switching effect is 10 milli-K, and it is not interesting for technical application. One shall use some other ideas for switching. Other idea was proposed by Leonard Tagirov and Alexander Golubov in their theoretical work from 2003. This is indirect switching. Actually, they used usual spin valve. In semiconductivity, it was already construction of spin valve, but using, instead of metal film, superconducting film between two ferromagnetic layers, and pinning layer, antiferromagnet layer to fix the magnetic configuration of hard layer. So, and this is the spin valve which was proposed based on triplet pairing. In non-conventional superconductivity, if you have non-collinear magnetization of two ferromagnetic layers, it can appear not only singlet, usual singlet BCS superconductivity, but triplet component. Some part of Cooper pairs will transform in the Cooper pairs with collinear orientation of spins, or triplet Cooper pairs, and such. So, okay, such triplet component is long living. It can penetrate in ferromagnetic layer, and the peculiarity of this component, this is theoretical calculation made by Alexander Golubov, Mikhail Kupriyanov, and Leonard Tagirov, our partners in this project, and Golubov is partner from Twente University in this project. they calculated the critical temperature of such spin wave structure, and they found that if you have non-collinear magnetization, then the critical temperature will have the absolute minima. At collinear it will be maximum, at non-collinear it will be minimum. That's why not by destroying superconductivity, but by switching mutual orientation of two ferromagnetic layers, one can operate with critical temperature to switch triplet pairing or to switch out the triplet pairing. And this is the idea of experiment where one shall prepare superconducting layer, for example, niobium, soft ferromagnetic layer, for example, copper nickel or palladium iron, some kind of soft ferromagnetic layer where with a very low magnetic field one can change its orientation. Then spacer to separate soft and hard ferromagnetic layer, hard layer, for example, cobalt, and anti-ferromagnetic layer to pin the orientation of magnetization of hard layer, for example, cobalt oxide. And such metamaterial can serve as spin wave. Switching on external field high enough to make orientation both of ferromagnetic layer collinear, soft and hard. Then reducing external field, the soft layer which has intrinsic magnetization out of plane, copper nickel alloy has such peculiarity that intrinsic magnetization is out of plane. That's why if we reduce external field to zero, then it will restore intrinsic magnetization out of plane. But hard layer conserve its magnetization in plane. That's why at zero external magnetic field, it will be non-collinear configuration of two magnetic layers. Then if we make reversal external magnetic field, soft layer can change its orientation of magnetization, hard layer conserve its initial magnetization. So it is easy to draw such picture, but it is difficult to prepare such multi-layer system, and this is a technological process which a lot of parameters which one shall investigate the influence, and if we would like to prepare the good quality of structure, what means good quality, with good interface, one layer should be separated from another layer. It should be no visible interdiffusion. Otherwise, all effects will be smeared and no triplet pairing will be detected. That's why we developed, on the base of existing vacuum technology, we developed a vacuum process based on magnetron sputtering with high deposition rate using amorphous silicon sublayer to prevent penetration of impurities from substrate. Who deal with vacuum technology knows that the most dangerous impurity is water molecules. they have a very strong adhesion to substrate. That's why it is very difficult to avoid penetration of water molecules in growing films, and they will spoil of the superconducting films. To prevent the penetration of such impurities, we use amorphous silicon sublayer. Like snow, it will cover absorbed molecules of oxygen or water, and on the fresh deposited amorphous layer, one can grow the multi-layer structure good quality. It is only one example of only one parameter which one shall control. There is a lot of other parameters: temperature of substrate, deposition rate, the residual atmosphere, a lot of parameters which one shall take care and control. It is described in this book, but for optimization of technological processes, what one shall spend a lot of time, and it is rather expensive because vacuum processes are very slow. For example, one shall heat the vacuum chamber one day just for desorption of the absorbed molecules of residual gases in vacuum chamber. That's why if you would like to change only one parameter, so for example substrate temperature, you shall spend some weeks for such attempts to gain knowledge about the optimal temperature or about optimal deposition rate and so on. That's why we choose another way, so-called smart technology, combination of the multi-level mathematical modeling of the vacuum process, and then on the base of this modeling, optimization of the vacuum process, and then to check the obtained parameters in the real experiment. Professor Alexander Vasilievich Vakhrushev from Ijevsk has many decades experience in modeling of various complex nanostructures, and we discuss with him our tasks to accelerate the process of optimization using such modeling, mathematical modeling of these processes. And he made modeling of the deposition processes for optimization of some important parameters. And the result of such modeling is presented in this nice picture. His group made mathematical experiment. It is vacuum deposition, but not in the vacuum chamber, but in the computer. And he varied substrate temperature, one parameter. Other parameters were fixed: deposition rate, or vacuum, or metals which we use. Only one parameter to change, and one can see how developed the interface between two layers. This is niobium layer and cobalt layer, superconducting layer and hard ferromagnet layer. As I told previously, that for a vacuum element, it is very important to have sharp interface with minimal interdiffusion. One can see that increasing the temperature, the extension of this area of interdiffusion after 500 Kelvin, it is a very rapid process of interdiffusion, and it looks like alloy rather than multi-layer structure. And optimization of this process gave us temperature, this is near 300K. 300K has a sharp interface and at the same time a good quality of the surface. Here one can see the modification of coordination number of single crystals. Niobium is like text polycrystals, and these crystals of niobium has a coordination number which change also with variation of critical temperature. It is one can see that the quality of the growing films also changed. Here, this is also mathematical experiment vacuum deposition of these layers, niobium and cobalt, and this is a cross section within the plane of the layer. One can see distribution of coordination number in the film which will be deposited at such conditions. And here one can see this is the free atom model, deposition of the niobium and cobalt, and the result at 300 and at 800 K, one can see the big difference. That's why such experiment saved us at least 2 months of work. We don't need to make deposition. We just see what will happen at such deposition. Here it changed. Here it was fixed substrate temperature and variation of the deposition rate, and also how does it change the quality of interface of deposited metamaterial. So, and using such powerful instrument as mathematical modeling, we can more rapidly develop the vacuum technological process and prepare such functional structure. It is a real structure. Previously, I showed you a slide with the sketch of the spin valve structure, and this is a real structure of the commercial silicon substrate. We use cheap commercial substrate because I told that the main goal of the project, development of the elemental base for computer, and it should be based, should be compatible with existing vacuum technologies, which usually used wafer, silicon wafer as substrate. To avoid oxidation or penetration of absorbed gases or water molecules, here one can see silicon buffer layer, then cobalt layer, cobalt oxide antiferromagnet fixing layer, soft ferromagnet copper nickel, vacuum element of the spin valve superconducting layer niobium, and then cap silicon, amorphous silicon to prevent oxidation, because the vacuum superconducting element should work many years without change of its parameters. For this purpose, one shall conserve the prepared structure. Conservation layer is amorphous silicon. After opening of the vacuum chamber, amorphous silicon will be oxidized by atmosphere oxygen, and very stable silicon oxide will protect the whole structure for further manipulation and use. So one can see here the high resolution transmission electron microscopy. This is the single atomic layer of single crystal substrate, and here the structure of the deposited films. And this is the superconducting properties of, here one can compare the theoretical calculation made by Sasha Golubov and Leonard Tagirov and Misha Kupriyanov, how critical temperature depend on the mutual orientation of layer anti-parallel, non-collinear, parallel magnetization, and critical temperature change. And this is in the real spin wave structure, which I demonstrated in the previous slides. One can see the absolute minima of critical temperature at non-collinear configuration when triplet component appeared due to non-collinear mutual magnetization. We guess that it is non-collinear, but to check whether it is real non-collinear, we used direct measurements in just a moment. This is experiments in Max Planck Institute. Yuri Gaidukov made our spin wave structure using reflectometry of polarized neutrons. One can see that non-collinear to collinear switching between these two configurations of spins. This experiment allows us direct checking the configuration of magnetic layers of spin wave. That's why it is direct and powerful instrument for investigation of magnetic configuration of metamaterials or spin wave structures. So, and this is memory effect. Just a moment. This is switching of such spin wave structure using pulses of external applied voltage. That's why one can use this element, but nevertheless the magnetic field, it is not low enough. That's why now we discuss with Professor Golubov and Professor Kupriyanov possibility to use the current to switch spin wave. Such structures which was calculated using the Josephson contact with magnetic metamaterial between two superconducting thick films, and switching such element not only using magnetic field but using the current to operate with such element. And this is the Josephson spin wave functional element, which was made in Professor Krasnov laboratory last year. Our collaborators from our institute worked several months, as I thought. There they learned the experience of the Krasnov group using focusing ion beam technology, FIB technology. It allows to cut several nanometers holes in the deposited multilayer structure, and from in plane one can use sharp focusing ion beam and to cut the Josephson junction with weak link from multilayered magnetic metamaterial. This is magnification of the of the Jerusalem Junction weak link area. And this is a real scanning electron microscope image of such element. One can see that it is rather good and rather sharp prepared thing. Okay, good. Summarizing the information which I presented to your attention, one can see that it was elaborated a smart technology based on the mathematical modeling of vacuum processes. Then vacuum processes were optimized and fabricated hybrid multilayered nanostructures superconductor ferromagnet, detected triplet pairing effect and spin wave effect, and such element can be used for organizing of a network, a big number of such elements connected with artificial synapses. This element can serve as artificial neuron, and connecting with artificial synapses to the neural network, one can construct the non-Von architecture of calculator. And the ideas, as I told, are summarized in Functional Nanostructures and Metamaterials book published in SPINTECH. Thank you for your attention, and if any questions, you are welcome. Yes. How we can yeah.
If somebody wants to ask.
Yes. So please, давай ты спроси для затравки. Your question, please.
Okay, yes. What will be next step? What do you want to achieve in the near future to improve this?
We just prepared this Jerusalem junction with weak link based on magnetic metamaterial, and we need investigation of its parameters. First of all, using your SQUID microscope, we would like to combine spin polarized neutronography, which we are doing in Max Planck in Stuttgart, in Professor Bernd Hartkeimer group. Yuri Gaidukov makes our colleagues Roman Morar together with Yuri Gaidukov investigate directly magnetic configuration using neutronography. But another additional direct method of such investigation is SQUID microscopy. That's why the next step, we are waiting for possibility to make such measurements in your group. As soon as the authorities of Twente University will allow us to do, then we would like to make such measurements. And in collaboration with Долгопрудный, with Vasily Stolarov group, by the way, Professor Golubov is head of the group theoretical supervisors, so-called, in Долгопрудный. And this group conducted by Vasily Stolarov has similar facilities. That's why we can make measurements also there, when it will be really possible. Somebody else would like to ask? You're welcome. Please, we have 2 minutes more for the next lecture. And that's why you are welcome, and you can use this possibility to gain new knowledge, new information.
Okay.
Okay.
Yeah. Let's wait. Maybe somebody would like to ask. If not, then we can finish your presentation.
Yes.
And next talk will be done by Hans Hilgenkamp at 10. So we have now a small break.
Okay.
We have a 5 minutes break, and then we have next
Okay,
lecture.
dear colleagues, after 5 minutes, we will switch to the second lecture given by Professor Hilgenkamp. You are welcome to the next lecture in 4 minutes. Okay. Okay. Thank you. Thank you.
There are other problems that we have to solve. So it's not downscaling in particular that is the ultimate goal, making things smaller and smaller. But there are other problems, and the main other problem is in the energy consumption. So the chips, they use an enormous amount of energy, and this produces a lot of heat. And removing all this heat from these chips is becoming a real technological problem. And for this reason, already about 10 years ago, the semiconductor industry has kept the clock frequency at a constant value. So these chips, although they could operate at let's say way beyond 10 gigahertz, typical clock frequencies are in the order of 3 to 4 gigahertz, just to help in keeping the temperature low. And also cooling, of course, is it has to be really done actively. You have big fans on top of these processor chips, and if you remove them, like in this picture, within seconds, you will see that it starts to smoke, and the computer will go down. Also, environmentally, this is becoming a big issue. Several percent of the world's energy is going into information technologies, and with the increase of the use of information technologies, for example, in the Internet of Things and self-driving cars and artificial intelligence applications, we will be using more and more information technologies, and therefore also more and more energy. And this energy problem is really a key problem. I hear some background noise every now and then, so if you don't have your microphone muted, it may be a good idea to just mute it to reduce the noise a little bit. And so energy is the big problem, and this was already addressed by Anatoly in his talk, that in these big data centers that you have around the world, and this is an example of a Google data center in Sweden, I think, you see that these are built at remote locations, typically at a place where it's already quite cold, so that it makes it easier to cool it down, where there's a lot of energy available to use in these data centers. But it's just an indication what a problem it is to deal with this energy use in information technologies. Actually, it's interesting to look back at this quote. What you see now is a tendency that computing is done at these centralized locations, these big data centers, and you know, at your workplace, you become more and more connected with the cloud and with these centralized computers. And in that sense, the quote was not so wrong, that on the world market, there may be this very big centralized computing system to which we are all connected. 5 may be a bit of a low number, but it's interesting to see that there is a tendency now, instead of decentralized big computing system, to go to centralized systems. But at the same time, there's also an increasing interest in what is called edge computing. So this is little computing devices close to a sensor, for example, where data is already processed directly where it's measured. Sometimes at places where connection with the internet is very limited, or where, because of privacy reasons, for example, in medical applications, You don't want to send around all this information via the internet. So also there is an interest for energy efficient devices, small computing devices that can be integrated in sensors for what's called edge computing applications. And so there are paradigm shifts in computing where energy plays a big role. Now this is a nice image to show that you have the IBM Watson system in Yorktown Heights as an example of such a centralized computing system. It's a big room filled with computers, programmed in such a way that it can solve a lot of questions, and you can just connect to that system. Even now also in a quantum computing form, you can connect to centralized computers somewhere and have them run a task. So we're moving to new forms, including centralized and cloud computing, but energy consumption is still a major concern. And in the Netherlands, this was big in the news this week. Day before yesterday, a very new big wind park was opened, the biggest wind park in the Netherlands, just a little bit north of Amsterdam, with 82 windmills, and in total they can produce the energy needed for almost 400,000 households, so that's basically half of Amsterdam. But in fact 75% of this energy goes to a new data center of Microsoft. So we're building our small country full with windmills for green energy. At the same time we're using all this energy for these data centers, and this is a concern, because also, for the well-being, for the people, you want to invest in green energy, but you don't want it all see dissipated in these energy consumptive technologies. So what is needed is research on new forms for the short term, but also for the longer term, where ultimately this issue of energy consumption can be addressed. And superconductivity can play a role there. It's not directly on the short term, but there is a lot of prospect, and I think it makes a lot of sense to think about, what could you do with superconductors that could solve this problem. And this is done also at various places around the world. This is a graph from an American program from the IARPA agency that ran a program a few years ago, the so-called C3 program, where the idea was to work on superconducting concepts to basically do something that is comparable to what a big supercomputer, semiconductor supercomputer can do. And so in terms of performance, it's quite comparable. But you see, for example, in the energy use, there is a factor of 100 potential improvement in using superconductors, because of the fact that with superconductivity you can make electronics that you can switch at much lower energies. In addition, for example, the area can be much smaller. You can make more dense structures because you don't need so much area to accommodate for all this heat production. So devices can also be placed closer together. Of course, there are drawbacks. You have to cool it down to low temperatures, which also is a technological problem. But if you do this in a big system, somewhere on a location where facilities are well installed for this, this should not be a big problem. Think about CERN, for example, and the enormous amount of liquid helium that is used there. It's something you can deal with. Now, superconducting electronics makes use of typical superconductivity aspects, and one of the most beautiful aspects and very useful for this purpose is the flux quantization, as was discovered by Alexei Abrikosov in the 50s. The fact that in a superconducting ring or in a superconducting material, you have if you go around a certain area, the order parameter, the wave function, can change only by a multiple of 2 pi. And if you enclose a magnetic flux, that means that the magnetic flux that you enclose is quantized in terms of a flux quantum, so a unit of magnetic flux. And this was imaged later on in various experiments, and it's a well understood and well appreciated phenomenon, very particular superconductivity because of the macroscopic phase coherence of the wave function describing the superconducting state. So these flux quanta can be used as a carrier of information. There is a difference whether you have, let's say, 0 flux in such a ring or 1 flux quantum, and the flux quantum can be in different directions, or maybe even 2 flux quanta. And how many of these flux quanta you have in these rings and their polarities can be, let's say, a way to encode information. And if you can switch these states very quickly, and you can do this by making use of Josephson junctions, I'll come to that in a minute, you can build up electronics with that. So that was the basis for the development of RSFQ superconducting electronics at Moscow State University in the around the group of Likarev and co-workers, and many of the people I think involved in this workshop are connected to some extent with that development at that time. And the fact that you in a superconducting ring, here is a superconducting ring where you have 2 Josephson junctions with the appropriate injection of currents, you can switch the voltage, the flux state of these rings from having a magnetic flux quantum inside or having no magnetic flux quantum inside. And these flux quanta, they enter and leave these rings via these Josephson junctions, and they can actually be switched in a transmission line circuit to a next ring, and in this way be transported in these RSFQ devices. And you can build up logic with this, where the advantage is that the switching happens very fast in the picosecond range, and also at very low temperature, at very low energies in the 10⁻⁹ joule range, which is really much lower and much faster than semiconductor electronics. So there have been a lot of developments, and I think the most advanced ones are in Japan, in the group of Akira Fujimaki in Nagoya, where they make quite complex processor devices with, let's say, several 10,000, or in this case, several thousand of Josephson junctions, but they have more advanced versions going up to almost 10,000 Josephson junctions, where you can process information at relatively low powers. It is still quite complex, though. The reproducibility of the technology has its limits. The fact that you have rings doesn't really help. If you look at semiconductor transistor, it's just a little, let's say, line element of a couple of, let's say, 10 nanometers. In superconductivity, you're always dealing with ring structures, and you're quite quickly approaching length scales of several hundreds of nanometers. So to make a real dense structure is quite complicated, and you have to make a lot of chips and connect them with each other. Nevertheless, you can demonstrate very fast operation. 750 gigahertz has been demonstrated for these RSFQ devices at very low dissipation levels. So it really allows new functionalities. Now, one additional complication with these superconducting rings is that the natural energy landscape is not so ideal. So if you look at, let's say, the lowest energy state of a superconducting ring structure, it's a state with 0 magnetic flux. And then there is the state with, let's say, 1 flux quantum inside, or the flux quantum oriented in the other direction. That's a state which is basically not the ground state, because you have a magnetic flux incorporated, but it's a state with a somewhat higher energy. And for binary logic, this is not so ideal. You don't want to have a logic element that you want to switch between a 0 and a 1, where the 0 has a lower energy state than the 1. And more ideally, you would have an energy landscape like this, so that you have 2 states between which you switch. And the one is encoding for a 0, the other one for a 1. And you switch back and forth in the appropriate way. And this is actually the kind of energy picture you would like to have for an element from which you build up a logic circuit. And in RSFQ technology, they actually do this. They create this energy landscape by injecting additional currents. So you have at different places in these RSFQ devices. In this case, you have a device built up of two rings. This is a flip-flop device. But you inject in addition to an input voltage, you inject currents. And the only reason why you do this is to tilt this energy landscape, to create a situation where you have these two lowest energy states at a somewhat equal energy. And this creates a lot of asymmetry in these devices. So if you also look at the design parameters, for example, for these junction junctions and the inductances in these devices, they're all different. All these junctions in their design need to have a different critical current. All these arms have different inductances, and you have this asymmetrically injected current. So the fact that you want to tilt this energy landscape creates a lot of complications technologically, because you have to control all these different parameters, and they're all different. And in addition, you have these additional bias lines, these current lines that have to go somewhere to a current source with which you inject all these currents. So the wiring is also very complex. Now it works. People can make these devices, and you can see it works as a toggle flip-flop. So if you're at the input, you have a train of voltage pulses. Then in this device, there are circulating currents in these rings, and they switch back and forth. And the result is that at the output, you have in a flip-flop, you have two outputs. The first voltage pulse arrives at this output, then the internal state of the flip-flop changes, and the second voltage pulse arrives at this output. So this is the basic functionality of a flip-flop as one of the key elements for electronics. And you can make it, but it's not so easy. There's actually a way you can do about it, and that's the topic a bit of my talk here. You can make superconducting rings where you play a trick. You actually induce inside the ring an additional phase change. And you can do this in different ways. And the way we did it in the past was by incorporating a high temperature superconductor in these rings. So this is a classical superconductor like niobium, which has an S-wave autoparameter symmetry. And the high TC materials, they have a D-wave autoparameter symmetry, which we also established through the experiments that I will show you later on. But the consequence of this D-wave symmetry is that if you go around this corner here, you experience a pi phase shift in the wave function, in the autoparameter. And this pi phase shift is, if you go around the complete ring, you have to end up with a multiple of 2 pi. So this pi phase shift has to be compensated in some way. And the way nature can compensate this, if this ring has the right parameters in terms of inductance and dimensions, is that it produces spontaneously a half quantum of magnetic flux. So you have 1 pi, which is connected with this D-wave symmetry, and the other pi is connected with this enclosure of a half flux quantum. Remember that I said before, in a normal ring, you have a 2 pi phase shift connected with 1 flux quantum as a quantum of magnetic flux, the Abrikosov vortex, for example. But if you build in a ring a pi phase shift, you basically have to compensate for this pi phase shift by making a half flux quantum. And this half flux quantum can be either up or down, which means you add up this pi phase shift to the one arising from the D-wave symmetry, then you end up with 2 pi, which is fine. Or you subtract it and you end up with 0, which is also fine. So that's the new ground state of this ring, is a state where you have a half flux quantum up or a half flux quantum down. And if you look at it in the terms of this energy landscape, then automatically you get an energy landscape like this. So this is the energy landscape of such a pi ring with a half flux quantum down as one of the states and a half flux quantum up in the other state. And these are the two ground states of the system. So the zero energy, the zero flux state is not a low energy state. It's actually a state which is higher up in energy. It's not favorable to have zero flux. Now we can make these kind of structures by making these so-called ramp type junctions, where you have a high temperature superconductor here. You have an insulator layer to define the junction well. And normally you would then make a connection to niobium, maybe via a gold layer. But we found that if you do that just like that, the interface is not very good. So you have a lot of damage here at the interface of the yttrium barium copper oxide, the high temperature superconductor that you structure with ion beam etching. And the transparency of this interface is very low because of a very bad layer here at this interface between the high temperature superconductor and the gold. But we made a little trick. So after etching here, we deposit a very thin layer, just a few nanometers of yttrium barium copper oxide again, and it kind of restores this material. So here was the original interface as we made it with the ion beam etching. This is this additional very thin layer that you grow on top, and you see that very nicely this material is recovered so that the interface with the gold is very transparent, it's very nice. And actually the film is so thin that here on these parts, it does not become superconducting. So only here where it's grown on top of the other superconducting layer, it becomes superconducting, and that's exactly where you want to have it. So this was a trick that helped us to enhance the critical current density of these high TC, low TC contacts very much to very high values, which allowed really to do practical experiments. We made these kind of structures, corner structures, and if you now look around the corner, just think about moving around the corner here, you see that, you know, when you go around this corner point here, you experience this pi phase shift inside the high temperature superconductor, and it should then be compensated by a flux or half flux quantum at these corner points. So at every corner point, you expect a spontaneous generation of a half flux quantum, and this is something that we could image together with John Kirtley and Cheng Tsui with the scanning squid microscope, which at that time was still at IBM Yorktown Heights in New York, but meanwhile it's in our laboratory here in Twente, the same system. So indeed you see that at all these corner points, you see magnetic flux arising, and we could calibrate that this flux was really a half flux quantum. So this was also an ultimate proof that the high temperature superconductors were indeed D-wave superconductors. After these measurements, there was no discussion about that anymore. We can do this with a lot of different elements. So we fabricated devices where individual corner junctions were fabricated in a kind of 2D array structure with almost 100,000 of these elements on one chip. And every dot here that you see is a half quantum of magnetic flux. And you can do all kinds of experiments measuring, for example, the magnetic coupling between these half flux quanta. And we have a few papers on this, but I don't go into too much detail here. Actually, if you do this measurement, you go with a scanning probe technique, scanning squid microscope, so a very small squid. You go over this sample and you measure all these different flux states. But you can also say, okay, let's cool down the whole array at a certain magnetic field so that all these half flux quanta are polarized in one direction. And you select a few specific elements, and with an external little magnet coil, you flip the flux states of these elements. And in this way, write information. And this is something we also demonstrated here by the example of writing IBM plus UT for the University of Twente in these arrays. So every element that you see here, either up or down, is a half quantum of magnetic flux, and the distance here between these elements is about 12 micrometers. So it's not ultra dense, but it's a form of superconducting memory that is also very, well connected with these RSFQ concepts, where also flux quanta are the unit of information. Now we incorporated these kind of high TC, low TC ring structures, these pi shift structures in these kind of flip-flop devices. So this was the picture of the classical flip-flop with all these additional bias lines. Now, if you use these pi phase shift devices, if this is a ring where you have this built-in phase shift because of the D-wave symmetry, and you have this spontaneous half flux quantum of magnetic flux, you don't need these additional bias lines anymore. Spontaneously, these rings have these circulating states. And in a flip-flop, you have two of these rings close together, and there are good reasons from a design perspective why you want to do this. But both rings have this built-in pi phase shift. So this is a half flux quantum with a circulating current in one direction, and this is a half flux quantum with a circulating current in the other direction. If you now apply a voltage pulse at the input, you see that there is a current then flowing from this input to ground. It divides itself over this structure. And you see that this junction then gets some excess current, adding up to the circulating current. This one switches, and also here on this ring below, you have some adding of currents here, and this one switches as well. So these two junctions will switch briefly to a voltage state, and this means that at this output there is a voltage pulse. At the same time, inside these rings, these half flux quanta, they change their polarity. So there's a flux quantum entering these rings, and the next state is a state where these half flux quanta have the opposite polarity. And then for the next pulse, you see that this junction and this junction switches, and there's a voltage pulse on that side. So that's the functionality of a flip-flop. Again, switching back to the initial state, so that when you have this train of input pulses, it divides itself over these different outputs, exactly the same as the flip-flop device that is fabricated with classical technology, but now without these additional bias currents. And we could demonstrate this in this paper. This is the ring structure. You see it here, and with the half flux quantum state stored into it. This is an input device, which is basically a device where if you have a sawtooth signal, that every rising ramp, it generates a pulse, a voltage pulse, an RSQ pulse, which goes into this transmission line structure, and that is this structure. And it enters at the input of this flip-flop. And then there is an output circuit that can read out the state of this flip-flop. And we could show that it really functions as a flip-flop. So you see it here at every rising ramp of the input signal here that you put in here. There's a pulse going into the flip-flop, and the internal state of the flip-flop changes. So at every rising ramp, you see a change here of the state of the flip-flop. So this was the first demonstration of superconducting electronics according to these RSFQ principles, making use of combinations of high TC and low TC superconductors in much more symmetric devices as compared to the standard RSFQ. And so that's the advantage of using these pi phase shifts. It becomes inherently symmetric. It reduces these bias currents. In that way, it also has a much lower energy consumption, a lower area that you need. And actually, you can tolerate also a bit larger variations in typical parameters like the Josephson junction critical current. Now, we've done this now with the demonstration of these combinations of high TC and low TC superconductors. But there are other techniques as well to create this pi phase shift. You can make use, for example, of magnetic materials. If you have a superconducting ferromagnet superconducting Josephson junction, so-called SFS junction, relating also to the previous talk. These SFS junctions also have these pi phase shift effects, which may actually be more advantageous than using these combinations of high TC and low TC superconductors, because you can make smaller structures from a material science point of view. It may be easier, but this is just a demonstration that making use of these pi phase shifts really brings advantages in superconducting electronics. Now, we've done these experiments that I just showed you a couple of years ago, and in the meantime we did some other things, but just recently Michael Faley and co-workers at the Forschungszentrum Jülich started picking up on this concept again, and they have very nice tools for fabricating these devices. So this is a picture from a chip that he made together with some of our students last year in Jülich, where you have very nice e-beam lithography patterned low temperature superconducting wires connected to the high temperature superconductor, and making these pi rings here with this very advanced technology. With the interest also to make superconducting electronics, but maybe also qubits for quantum computation. They've made nice array structures where you have many of these rings closely together. you see here, that many of these elements in these arrays. And we looked at some of these samples with the scanning squid microscope in Twente, and you see that all these rings produce magnetic flux, and we can see that this is a half flux quantum of magnetic flux. There is a bit of distortion in the picture because of the imaging technique, but that it's basically just a picture of the magnetic flux states of these arrays. In this case, the chip was cooled down in a moderate background field, so all these half flux quanta have the same polarity except for one stubborn one, which had, because of some fluctuation, had the polarity in the other direction. But you can play with this distribution of up and down half flux quanta if you cool down at different magnetic fields. And these are some more elaborate structures where you have, let's say, coupled elements, have two of these rings close together, and you can see that they form an antiferromagnetic pair. This is just one ring, that's this one. But we can also make structures with a bias current line so that you can actually play with a bias current and force switches in these devices by flipping the polarity of these half flux quanta using these bias currents. And this is an example where you see that if you change the bias current, you sequentially flip from, let's say, the state where you have, for example, two down oriented rings to the state where you have an antiferromagnetic pair to a state at higher bias current where the polarity of both have flipped to the other direction. And you expect it, this hysteresis that you also see here in this device. So what it means is that besides our work in Twente, there's now another group in Jülich fabricating high quality, high TC, low TC structures, showing also these pi phase shift effects and the formation of half flux quanta as a basis for superconducting electronics or quantum electronics. They've now moved from niobium as the low temperature superconductor to molybdenum rhenium. And this is a nice material. It's also a low TC superconductor, but the Josephson junctions are even better than with niobium. You have higher critical currents, higher ICRN products. And so from a material science point of view, there seems to be an advantage in going from, let's say, IPCO niobium to IPCO molybdenum rhenium contacts. And so also there is progress. And this is ongoing work together with Michael and his co-workers, where we are studying connected arrays. And so in the previous picture, like here, you see that these elements are magnetically coupled to each other, but not electrically, and they're electrically isolated. And that's also what we did in earlier experiments. But we're also quite interested to see what happens if you have electrical connections, shared strip lines between these different elements, and creating in this way arrays of coupled fractional flux quanta, and see if we can manipulate them in some way. And this is how they look like in the picture. Unfortunately, we have some hiccups at the moment with the scanning squid microscope, so we don't have actual data on these coupled arrays, but this is work in progress. So I expect that at some point we can show also the magnetic activities of these arrays and see if we can use these electrical couplings between these elements also for electronic circuitry. This is another picture where you can see that these chips look already quite advanced. So that brings me a bit to the end of my talk. I'm not sure how am I doing in time. I think it's quite okay. So there have been a lot of people involved in the work that I've showed. A lot of students, current students and previous students at the University of Twente. Also at my previous places, Augsburg and IBM Zurich. John Kirtley, Cheng Tsui at Yorktown Heights. Some students in particular that went on internships together with Michael, or worked together with Michael in the last experiments with Forschungszentrum Jülich. And if I just have a little outlook on how things may develop further, so we are studying these half flux quanta, and we look at new forms of superconducting electronics. The pi phase shift devices in RSFQ. But you can also think about using these concepts in more these brain-inspired electronics that were already introduced by Anatoly. Think about neuromorphic computing using superconductors or using these fractional flux quantum effects, qubits. There are concepts called MEM computers. Deventra in Santa Barbara is looking into these things. So these are more concepts where instead of having logic gates with inputs and outputs, you have logic gates where the inputs and the outputs, it's combined. So an input is both an input and an output at the same time, and you build up arrays of these elements, and it's a kind of self-organizing network, which is somewhere in between standard logic and neuromorphic circuitry. Just Google MEM computing and you'll find all the information. And also you see that these half flux quanta, they look quite similar to what people do at D-Wave in Canada, where you have ring structures biased with flux in such a way that actually the ground state becomes this degenerate state of two fractional flux quanta or two flux states with opposite polarities. And that looks quite similar to these arrays as we are studying them. So I think there's a lot of prospect in using these pi phase shift devices, both using these high TC, low TC combinations, but also other technologies like the superconducting ferromagnet superconducting structures. Okay, I think that's what I wanted to say now. I'm open for some questions. Thank you very much.
Okay. Thank you, Hans. Thank you for nice presentation. Yeah. Let's questions maybe. Somebody wants to ask. Anatoly, maybe? Yeah. Mm-hmm. Are you unmuted? You can speak here.
Hans, thank you very much for the interesting and informative presentation. I would like to ask you about the nearest perspectives of the brain-like neuromorphal computing structures.
Mm-hmm.
Which way, to your opinion, is preferable?
Yeah, that's a good question. So you see that in let's say, semiconductor technology, there's a big interest in these neuromorphic concepts. It's connecting, of course, also with artificial intelligence. So you have these artificial neural networks as the basis for new applications, where you have the possibility to train a network for specific tasks, like image recognition, for example. And semiconductor technology is doing a lot of these things. There are nice demonstrations where neural networks can play games like Go and these kind of things. That costs an enormous amount of energy. So to train these neural networks is an enormously energy consumptive task. So the semiconductor industry is looking for development of chips that are really specialized for these tasks. So in the past, you had these central processing units, CPUs, that have a kind of serial way of working. Then you got these GPUs, graphical processing units. They work more in parallel. Now you have tensor processing units. That's a new development where the chips are fabricated in such a way that they can allow matrix multiplications and more parallel developments. And the next step for the industry is what is called in-memory computing, where you don't transfer information from memory to a processor, and that's the von Neumann concept and the von Neumann bottleneck, but that you do matrix multiplication tasks already in the memory device. And for this, you need new concepts for hardware that you can combine with these memory devices, and then concepts like memristors come into view. Elements that you know can be used to work with these this information stored in the memory and get some output there. So the semiconductor industry is very much looking into concepts for these memristors. There are phase change materials and other devices, resistive switching devices. And of course, also there, the question is, about reproducibility, controllability, energy consumption. And if you want to do something with superconductivity in that direction, I think you have to look at something like that, where you combine superconducting memory with simple tasks like matrix multiplications, and see that you realize this, what's called in-memory computing with superconducting structures.
Thank you very much. Thank you.
More questions? I see Mr. Kuprianov here. Maybe do you want to ask?
Yes. Can I ask a question? Sorry.
Yes, sure. Yeah.
What do you think about the possibilities to use phi junctions based on Josephson structures with ferromagnetic spacers? Not hot temperature superconductors, but neobium-based technology with ferromagnetic spacers, such as Goldubin structures and so on and so on.
Yeah, I think actually that's the way to go. The things we've done with the high temperature superconductors are a nice demonstration of the potential of using these pi phase shift effects, but creating pi phase shifts, or what's called phi phase shifts, even fractionals of pi, in other ways, like in superconducting ferromagnet superconducting structures, I think it has more potential for technology. And there are a number of groups, and including some of your groups, are working on this. I think what is especially nice is the concepts that were, for example, created by Misha Kuprianov and co-workers, that you can do kind of spintronics with multiple ferromagnetic layers. So you can switch a Josephson junction from a situation where it's a pi junction to a situation where it's not a pi junction, a standard junction, by playing with the orientations of the ferromagnetic layers, which gives you an additional degree of freedom. You can choose whether a junction should be a pi junction or not by playing with the magnetization of different magnetic elements. In terms of neuromorphic computing, there are some interesting developments, for example, at NIST in Boulder, where they incorporate magnetic nanoparticles in a barrier. So not magnetic layers, but just little nanoparticles with their own magnetization. And then you can gradually align the magnetization direction of these different nanoparticles and gradually tune the critical current of the Josephson junction. So for learning applications in neuromorphic computing, this could be an interesting development, because you can step by step teach a Josephson junction, let's say, towards a certain critical current value, rather than just switching it between different values. And so I see a lot of future actually for these combinations of superconductors and ferromagnets in different ways.
Thank you for your answer.
Okay. More questions? Okay. So, Anatoly,
any more questions? Yes. Hans, thank you very much once again for presentation and extended explanations. Yeah, it is really useful for listener. I see that a lot of young listeners followed our summer school, and they gained a new knowledge, new information, and perspectives of further development. Thank you very much again.
Thank you very much. Good luck with the workshop. I have another meeting I have to go to, but I'll come back at some point later on in the program. So
thank you. Thank you again.
I apologize if I'm not connected,
yes.
but
just to remark, we have a recording, and then we will put the file. It will be available for everybody with all the lectures.
Yes, as we thought,
we do a video recording
in at the beginning, that later we will put the recorded lectures to the web page of our SPINTECH project, and it will be available, as Eurocommission asked us to to make it visible, and dissemination of results for as much as possible a listener and young researcher can gain this new knowledge.
Okay.
Thank you once again. And
We have a break now until 1 o'clock. And the next lecture will be done by Alexander Brinkman. Alexander, are you here? Online? What is he? Okay, he knows. So he will join at 1 p.m.
Yes,
Okay.
and we will continue at 1 p.m. Thank you.
Thank you.
Have a nice lunch. Bye.
And,
Bye.
Goodbye, and see you later. Okay, so recording started. Okay, so please start. So next lecture will be given by Alexander Brinkman. As you can see the title, Wismut-based topological materials for spintronics and topological Josephson junctions. Okay, please, you can start.
Thank you, Sasha, and it's a pleasure to be able to show some of our results on in this field, where we actually use now topological materials, mainly for the purpose of making topological Josephson junctions, but they might also find some applications in the field of spintronics. And I'd like to introduce both topics to you in this talk. After my talk, there will be the talk by Dr. Chuan Li, who will follow up actually on the topological Josephson part and showing how we actually measure the topological properties, etc. So the two talks will be combined, in fact. The work I'm going to show today has for a large portion been done by the people you see here. Some of them are PhD students that are still here. Some have graduated already, like Jorrit and Joris. And we have benefited from getting very good crystals, topological materials, from the University of Amsterdam, of this group of people. And some of the results I'm going to show you are done in close collaboration with the German Forschungszentrum Jülich. That is probably also familiar to you. What I'm going to show you today is that the nice part about using topological materials is that we can use the spin momentum locking that you have in these Dirac cones, whether it's 2-dimensional or 3-dimensional, for a number of applications. And in spintronics, I'll show you some results on the non-local detection of spin accumulation and the chiral magnetic effect. And in the superconductivity part, I'll make an introduction to the use of topological Josephson junctions. And to start with that, like, why are people in general interested in topological Josephson junctions? We have to look at the field of non-abelian anyons. You know that if you take two bosons, 1 and 2 here, and you would interchange them, the joint quantum mechanical wave function would be the same. If you interchange two photons, you get the same result. For fermions, this gives you the famous minus sign, of course. Like if you do this for electrons, interchanging two electrons gives you a minus sign. But in general, the indistinguishability of particles also would allow for a third possibility, namely that the joint quantum mechanical wave function gets an additional phase, which is not necessarily 0 or pi, but it could be anything in between. And that's where the name anyon is coming from any phase. And these particles have had people's interest already for quite a while. But especially in the context now of Majorana physics and braiding in the field of topological quantum computing, I think this field got a big boost, which I think is very nice for superconductivity, that there is this whole new types of Josephson junctions that could become important. In the end, what people are after is, of course, to create non-abelian anyons, and the anyons I've explained, but the non-abelian aspect relates to the fact that the order in which you interchange the particles, for example, here, I first interchange these two particles and then this one with the third particle. But if I reverse that order, I get a different wave function in the end. And that means that this is what people call braiding, this interchange of particle is a way of manipulating the wave function. That's what you do in topological quantum computing. And of course, the theorists at Microsoft, they are working already heavily on developing code to implement this in quantum software. So where does superconductivity enter the picture now? Well, we know, of course, that in superconductivity, we have quasi-particles that have electron-like or hole-like properties. Starting from the very basics, if you look at this electronic dispersion relation for a free electron in a metal, for example, we could equally describe the empty spaces. These are our antiparticles, these are the holes. And typically in a normal metal or in a semiconductor, you would take either one of these languages to describe your system. Otherwise, you're counting double. But we know that in superconductivity, if we switch on the pairing interaction, we open a gap at the Fermi energy. And in fact, now we have coupled our electron and hole description of these electron states in the material. If you now sit somewhere very close to this minimum here, you could argue that this Bogoliubov quasi-particle is half an electron, half a hole. And automatically, that would mean it's its own antiparticle. This is partly true. There has been some debate whether or not all the Bogoliubov quasi-particles are perhaps Majorana states. But what you need for a Majorana is that it's its own antiparticle. And strictly speaking, if you look at this electron and hole branch, you also have to take the negative energies into account. And you see that, in fact, annihilating a particle at energy E is the same as creating one at -E. That's the particle-hole symmetry that is in superconductivity. So basically, if you want to make this non-abelian Majorana anyons, what you need is to have a Bogoliubov quasi-particle sitting at 0 energy. And to do that, you need a topological Josephson junction. And this is where topology comes now into the play. So let's look at the topological materials. And the one that we started working on already 10 years ago is the topological insulator. And a topological insulator, a three-dimensional topological insulator, is insulating in the bulk, but it's conducting at the surface. And this has to do with a band inversion that takes place due to a very strong spin-orbit interaction, due to the very heavy bismuth in this case. And if you look, for example, at the electronic structure, this is an angle result photoemission spectroscopy picture, you see a bulk valence band. Here is still the glimpse of a slight bulk conduction band. These are the three-dimensional bands. There's a very big energy gap of about 200 millivolt in between, but you see that there are these linear dispersing states. These are the surface Dirac cones that you have at the surface of such a topological insulator. And a very nice feature of these surface Dirac cones is that the spin, the electron spin, is coupled to the momentum, meaning that an electron traveling to the right has spin up and an electron traveling to the left has spin down. And in this way, basically, we can create also spinless states, right? Because there's only, the degeneracy is lifted now. Of course, the other spins are there, but they sit on the other opposite surface of this three-dimensional topological insulator. I give the example here of bismuth telluride. It's a well-known material, and it's especially nice because the crystal structure has these quintuple layers of alternating tellurium, bismuth, tellurium, bismuth, tellurium layers. And in between these quintuple layers, there is a very weak van der Waals type bonding. And like people who have made devices on graphene, what you can do is you can very easily exfoliate these crystals and you get very smooth surfaces of these crystals. And they can be quite thin, several nanometers to maybe hundreds of nanometers thick. So you can do all your standard lithography parts to actually use these flakes of single crystals to make devices. You see an example here. This is a bismuth telluride flake, and this is even an electron beam structure that we made on these type of devices. For some applications, to use the single crystals is nice. They typically have quite high mobilities and very good crystal properties. But of course, if you think about future applications, and I mentioned the topological quantum computer, then of course we need thin films. And in fact, the growth mode of these tellurides, it's a very nice thermodynamic regime, which allows you also to grow very smooth films by using molecular beam epitaxy. Basically, you evaporate the bismuth and the tellurium simultaneously. And you see some scanning tunneling microscopy picture here where the individual atoms are visible. You see that every crystal step here is a nanometer high. This is exactly one such a quintuple layer. And if you do angle result photoemission spectroscopy on such a surface, again, you see a bulk valence band. The bulk conduction band is not visible here. It would be above the Fermi energy. And you see this linear dispersive states. If you look with the transmission electron microscope, you can see the high quality, in fact, of these crystal structures. If you grow them by MBE, again, you recognize this quintuple layer structure. And the quality is actually so good that if you now, for example, by an electric field or by doping, put in some charge in the bulk of the material, so you enter the conduction band, then you typically end up with quite high mobilities, indicating that there are very few defects in this structure. However, the surfaces are very sensitive to chemical reactions. So for any application, what we typically need to do is, before we make any device, we have to put a capping layer on top. An example, for example, you could put a tellurium layer or an aluminum oxide capping layer on top of the topological thin film, just to prevent the surface from oxidation. If you look again at the angle result photoemission data here, this is a picture that is taken in situ. So after growing the sample, you keep the sample in vacuum. In a vacuum suitcase, we transported it to an ARPAS chamber and we did the experiments. If you would not do that, then you would lose these nice surface states. That's very important. So you use this capping layer technology. And then, of course, you can gauge tune all the way through the Dirac cone, being on the electron side of the Dirac cone or on the hole side, until you enter one of these bulk bands. So these are the electronic properties, but I've not shown anything yet of the spin properties, but they can be measured quite directly. And this is an example of a quite complicated device that we made to actually show the spin momentum locking. And it looks as follows. You see here a piece of topological material in blue. There are some gold contacts just to be able to inject current into that material. The topological insulator is only conducting at its surfaces and not in the bulk. But we have put it on a sheet of graphene, because in graphene, we know that the spin lifetime is very long. A spin can diffuse over very long distances without being spin flipped. And then on several micrometer distances along this sheet of graphene, we use some cobalt ferromagnetic readout electrodes. And now what happens is that if we send a current through the two surfaces, of course they run in parallel here, you can see here the energy is function of K. You know that if you run a current to the right, there will be more spin up electrons than spin down electrons. So basically there is a spin polarization, and the spin polarization diffuses into the graphene. And inside the graphene, of course, it decays after some distance, but that's a very long distance. So over micrometer distances, we can still measure the spin accumulation. And the signal that we then pick up from our ferromagnetic electrodes, that you can see here, for example, in this graph, as function of the applied magnetic field. And then you clearly see that it switches whenever the cobalt electrodes switch. But also, if I now revert the current, so I apply here a positive current in some direction, and I see this spin polarization signal that is hysteretic. But if I invert the current, so I send it the other direction, you also see that the magnetic signal changes direction, right? This is a kind of sanity check that it's really due to the current in the TI that makes this spin polarization signal invert. And here you see the full dependence. If you go to too high biases, in fact, our signal decays because we believe we are in a non-equilibrium situation there. There was some debate quite early on in literature. What would actually happen to the spin polarization if you go from the electron doped side of a cone to the hole doped side? Would the spin invert or not? And in fact, if you think about it clearly, of course, it should not invert. And as a function of a gate, it's the right picture here, we can actually gate tune the Fermi energy through the Dirac point all the way from the electron side to the hole side on one of these surfaces. And indeed, you see that we have a symmetric signal. That's the black signal here, for example. And if we invert the current, we see an inversion of the signal again, irrespective of the sign, whether we are electrons or holes. So this worked out luckily as the theory predicted. But it showed us that this spin momentum locking is really there. Okay, that's about the topological aspect. Now, of course, we would like to combine topology and superconductivity. And the most natural place then to look is for some material that would be intrinsically superconducting and topological. And if you look into the theory, then what people predict is that you get, for example, this chiral p-wave order parameter symmetry as an indication of topological superconductivity. And if you make some NIS junction to probe the superconducting density of states, then instead of having this Blonde-Tinkham-Klapwijk type of gapped spectrum as you would have for an S-wave superconductor, this is what you would theoretically expect to see for a p-wave superconductor with some tunnel contact probing this density of states in the superconductor. So in literature, you now see this type of spectra popping up quite often as people want to prove that something is a p-wave superconductor. We've also worked on several materials that were predicted to be p-wave superconductors, but up till now, without any success. Although sometimes the spectra look surprisingly close to being p-wave, but they are not. I'll show you an example here. For example, here you see in the IDV spectrum, as function of the bias voltage, of a palladium ditelluride material. This was also predicted to be a topological superconductor. And to our surprise, we found something that looks pretty much like a p-wave spectrum. But we realized that actually all the physics was mainly due to our contacts. And there are some models that where you have a diffusive and a ballistic channel in parallel to each other. And basically heating plays a role here. And that if you do the experiment right, meaning that you have a much better insulating barrier here, a better tunnel barrier, then in fact, if we did it again, we had a much more S-wave-like conductance spectrum, showing that what we observed before was not related to the p-wave. But we were almost fooled by this, but I think maybe sometimes in literature, people are actually fooled by this. So if there are no topological superconductors around yet, then there's another way around of still getting this, namely by the proximity effect. So then we enter the field of topological Josephson junctions. And here is an example of why this is useful. You know that if you have a standard weak link with a normal metal in between two superconducting contacts, and we look at the Andreev bound states in such a Josephson junction, then these are for example, here I plotted in blue and pink. These are two possible Andreev bound states that sit there. They are 4-pi periodic states. Well, in practice, next to this Andreev reflection, there's always, of course, the probability of normal reflection in the interlayer. And as is very well known, you get these type of Andreev bound spectra then that are always 2-pi periodic. And this opening, this avoided level crossing here, it depends on the size of the barrier here. But the barrier could even be something like a Fermi velocity mismatch. It doesn't need to be very big. But now, again, the field of topology enters, because if we make the interlayer now of a topological material, it means that the spin-up electron cannot scatter back over 180 degrees, because it would have the opposite spin. And these are quantum mechanically orthogonal states. So the backscattering in this case, at least if you do it one-dimensional, it would be forbidden. And then in fact, what you end up with is again, just the crossing at zero energy. And as I told you before, if you make a quasi-particle state or an Andreev-bound state sitting at zero energy, so if I bias my Josephson junction exactly at pi, this would be a Majorana-bound state, which is interesting for the field of topological quantum computing. So that's why people study these type of topological Josephson junctions. And in the end, what people would like to do is not only make one topological Josephson junction, but you want to build a whole array of these type of superconducting islands. And then if you phase tune all the different islands, you can manipulate the conditions to whether such a bound state should sit here or not. It's like a Josephson vortex. We know that depending on the phases, there's either a Josephson vortex here or not. And in special cases, it sits at zero energy. So then it's considered to be a Majorana particle. And this was studied very early on already in this Fu and Kane paper. Of course, we realize now that this technologically might not be so easy, because you have to do it very fast. Every quasi-particle in the system would already destroy these states. So you have to do it faster than the quasi-particle poisoning time, basically, in these systems. And people have started thinking of how to implement that technologically. And I think for our community, what is interesting is that this could maybe be done by using rapid single flux quantum technology. So I've shown a lattice here where, again, you see these hexagons. These are all different superconducting islands, but now consisting of interlayers that are topological. So if there is a Josephson vortex sitting somewhere, then this would be this Majorana state. And in the end, what we would like to do, what you see in the picture in the bottom right here, you would like to interchange these Josephson vortices. But you know that in a lattice, if you send in current pulses, like you do with RSFQ, you actually move around this flux, right? That's what we are used to thinking of this. So if we could think of a way of implementing a kind of RSFQ type technology with these topological Josephson junctions and be able to operate this at very high frequencies, I think you might come close to what is needed to do this, this topological quantum computing. What is the advantage then is that we don't use flux biasing like Fu and Kane described. We use local current pulses, but this would still require that we can access all the different superconducting islands individually, which might also be technologically difficult unless we do some flip chip technology maybe. But you could also think about varying the distances between the Josephson junctions so that some of the critical currents are larger than others, so that you can use still global currents that are sent through the entire array, but then would only move around the fluxes that are trapped less strongly. So we thought about some mechanisms by which you can indeed do some braiding with some global current pulses. But all of this is still very far away future, because we still have to see indications of these Majorana states, but it's already nice to think a little bit ahead. And I mentioned that we closely collaborate with the University in Jülich, Forschungszentrum Jülich. And together with them, we developed some technology that should already be then as close as possible to what we need in this RSFQ type of structures. And one of the aspects is that you would like your electrodes, in this case we use niobium, to be deposited in situ on the topological insulator to avoid any degradation of the surfaces and to get a very good proximity effect into the topological material. So for that we use some shadow mask technology, and you see an example here where the bridge, the shadow of the bridge is actually forming the barrier, the topological barrier here. So there's topological material underneath, and you see the two superconducting electrodes here. The interface quality is quite good, so we get reasonable Josephson currents in these type of structures. But in this specific case, we found out that the topological insulator material is still a bit too metallic. So on top of the surface states that could contribute to the Majoranas, there are always some bulk states available also that they just add with Andreev bound states to the total supercurrent. So then if you look a little bit now across the globe and see what people are trying now in the field of Majoranas, you know that, for example, pioneers in Delft and Lund and Copenhagen, what people are trying to see is if you take a semiconductor nanowire that has a very strong spin-orbit coupling, and you induce superconductivity via the proximity effect, and on top of that you apply a parallel field to open a Zeeman gap, then you can also make this nanowire topological. And the advantage of a nanowire is that it's already somewhat one-dimensional. So they found already by doing the IDV spectroscopy, by looking at the zero bias conductance peaks, some indications for Majorana physics. And similarly, if you use mercury telluride, which is a two-dimensional topological insulator with one-dimensional conducting edge states that also have the spin momentum locking, in these type of Josephson junctions, people have also observed that the current phase relation is 4-pi periodic instead of 2-pi periodic, suggesting that indeed these modes cross zero energy and that Majoranas play a role. On the 2D surfaces of three-dimensional topological insulators, I've shown you some results that we did with Jülich, for example. Also there, some indications are there that one of the modes is 4-pi periodic, but all the other modes in different directions add to the 2-pi contributions. So that's already somewhat more difficult to see. If you now look at the dimensions, it would also be interesting into seeing what happens in the third dimension. Can we actually use three-dimensional Dirac semimetals to do the same topological trick? And to sketch a little bit what a three-dimensional Dirac semimetal is, it's best to look at good old bismuth. It's a very well-known material with very small electron and small hole pockets. But if you look at the band structure, the energy is function of the doping here. These electron pockets, this is pure bismuth. So you see that there is this pocket here, and much higher up you see that you get the valence band from these holes, from the hole pocket. But if you dope it with antimony, then actually these pockets, they shrink, and at some point you get a band inversion. And when you're above that band inversion, in fact, these pockets are topological. And okay, if you dope it even further, you remove completely the hole states. So then you enter the phase of the topological insulators. And this was in fact one of the first topological insulators to be discovered. But now we're actually going to focus more on this regime, where we have this band inversion. And sometimes this is called an accidental Dirac semimetal. So when we are underdoped, we have this structure. When we are in the topological regime, we have this structure. But at this transition point, we have a cone, a touching point here, a Dirac point, living in 3 dimensions. That's why sometimes it's called three-dimensional graphene. So in all the different dimensions, in all the directions, we have a linear dispersion relation. Of course, there are also surface states that you now have to take care of because they are non-topological. But we did some angle resolved photoemission spectroscopy on these crystals to see how large the carrier density contribution was. And I'll go a bit quicker through this, but you can study, for example, the Shootnikov-de-Haas oscillations in this doped bismuth so that you can know the contributions from the electrons, you can know the contributions from the holes and from the surfaces by studying the angle dependence. In the end, if you do all these normal state characterizations, what you found actually, so for our 3% doped bismuth, so 3% antimony in there, we found the transport to be dominated by the bulk electrons in the Dirac cone that have a very low carrier density. We are very close to the Dirac point, somewhere below 20 milli-electron volt above the Dirac point, meaning that the Fermi wavelength becomes also quite large. So this is interesting because it's predicted that in all these different directions, there should be still the spin momentum locking. And then it becomes even more interesting if you apply a magnetic field, because the Dirac cone is degenerate in spin. And if you apply a magnetic field, for example, in the parallel direction, then this degeneracy is lifted because the two cones will split into what are called Weil cones now. And on top of the splitting in magnetic field, if you now apply an electric field, you create a non-equilibrium situation in which one of the cones is populated more than the other cone. And this strongly influences the scatter rates in between. And it has actually been shown that you get a negative magnetoresistance as soon as you tune your electric and magnetic fields very close to each in the same direction. And this we could also show in our materials. So if it's perpendicular, for example, we have a very strong positive magnetoresistance, but it becomes strongly negative when you apply it parallel. And you can do some more fun experiments with this. And this is an example I like very much. So what we did here, we took such a material, we structured into a big Hall bar with multiple probes on the sides. And we applied the magnetic field parallel to this contacts. So that means that in the topological Dirac semi-metal, we now split the cones. And then additionally, if we apply an electric field here, by just a current bias, for example, we know that we populate one of the cones more than the other. So one of the helicities is more present than the other. And actually, this can diffuse this polarization along the Hall bar. So in this direction, you would still expect to be one cone more populated than the other. But if that's the case, and we enter all the other side on the other side of the Hall bar, if one cone is more populated here than the other cone in a parallel magnetic field, this would give us an electric field again. So also the contacts that are away from where we inject the current should develop some kind of Hall voltage, but in this case, parallel to the magnetic field. And this signal we probed over the distances. And then you can actually show that over micrometer long distances, this polarization of one cone with respect to the other, is a kind of valley polarization, is actually sustained. And in very fancy language, this shows that there is some coupling between the E and the B fields, right? This is this axion electrodynamics, what people are looking for. Okay, so in conclusion, I hope to have shown you that for spintronics, this spin momentum locking could be interesting because a current directly translates into a spin polarization, but that when you use a three-dimensional Dirac semi-metal, you have actually 1 degree of freedom more, namely that you can tune the polarization of one of the helicities with respect to the other, and then you enter the field of this, what's called the chiral magnetic effect. And of course, the spin momentum locking that lifts the degeneracy in spin that you have at these topological surfaces. And that's what people need to get topological Josephson junctions. So as an outlook to the talk of Chuan, this is typical devices she will talk about. And you see a flake of this material that I've been discussing, this 3% doped bismuth. And then by just putting on some sputter contacts and the niobium contacts, we can study the topological Josephson properties there. But for that, you will have to wait until Chuan's talk. So that's what I wanted to show you here. And I'm happy to take any questions.
Okay, Alexander, thank you for your talk. Yes, we have time for questions.
Alexander, may I ask you the following? When you try to make a Josephson junction, you deposit the electrode on the top of the isolator, and during this deposition, you change the structure of top isolator. And so the structure looks like that you have some two-dimensional top isolating properties in between, and very strange connection from electrode to this topological matter. could you have any hints who control the connection between this destructive area and the matter which we want to use or examine?
Yes, that's an excellent question. So you're absolutely right. At the position where our contacts are on top of the topological material, probably we disturb this topological surface state. But still, we get a proximity effect in that direction, meaning we have induced some superconductivity beneath the electrodes. And then what we believe to be the topological Josephson junction is actually in the lateral direction. So you could say we have some disordered, at least there is a superconducting proximity effect. And then laterally, it has to cross this topological barrier. So in that sense, we can make use of the topological properties. But you're absolutely right that we don't completely understand what is beneath the electrodes. And what we would like to study, for example, is whether there are p-wave correlations there or not. But I think in this case, it's very difficult to do this in this perpendicular geometry. So of course, we have tried to induce the superconductivity laterally, but then the cross-section is also very poor. So I think it's an open question of how to do this best and whether it's needed or not. But it's a very good question. You know that in the field of, for example, when people do this with the semiconductor quantum wires, also there, they made big improvements when they started to deposit the superconductors in situ. And of course, with Jülich, we have been doing this also, deposit this in situ. But still, we noticed that the superconductors, they also dope just by electron doping the material beneath. So probably we are not in the Dirac cone alone, but there's also some bulk conduction right beneath the electrodes. So laterally it's okay, but you're absolutely right. In the perpendicular direction, it's more messy. Yeah.
Thank you very much.
Okay. More questions? Okay. Well, since we don't have any other questions, so let's close this talk. Thank you, Alexander. And we have a break now until 2 o'clock. So 20 minutes break. Then Chuan Lee will continue. Alexander already announced the subject. It will be basically extension of your talk on the same topic.
Yes, on
okay.
The topological part.
Thank you all. Yes, so then I will pause the recording.
Okay.
And yes, okay, it's now recorded. Okay, so I think now many people already joined. So please start. So next lecture will be done by Chuan Lee. And
Yeah,
so please.
I'm going to share my screen.
Yes.
Yeah, okay.
Okay.
Full screen. Okay.
Okay, yes.
I think that works.
It works, yeah.
I will put you small. Okay, thank you everybody. I'm very glad to be invited to give a small talk about quantum devices towards 1D topological superconductivity. And this work is mainly done with a collaboration between multiple groups. And there are 3 PhD students working on this project, worked on this project in Twente, besides Joet and Joret, Alexander introduced, and also Bob Dawn, who was mainly working on the superconducting devices. And besides University of Amsterdam and the Jülich Center, we also have a lot of collaboration with Beijing University, with Professor Zhenmin Liao's group, and especially Cai Zhen and Anqi, these 2 students, contribute a lot on the subject I'm going to present. So this is outline of my talk. I'm going to give an overview or some review on this induced superconductivity in topological materials, and then I will show you the results we had on bismuth antimony and another type of another 3D Dirac semi-metal material, cadmium arsenide. So first, I think Alexander already had quite nice introduction about this part, that we want to have Majorana states using the electron hole particle symmetry. And so we usually employ this superconductor in our device. And then we're gonna deal with this spin rotation symmetry in the system. So basically we have two choices. One, to have a special intrinsic spin triplet Cooper pair superconductor. That's a P-wave superconductor. However, this is very rare in nature. And so far, there's no strong evidence to confirm the material in this type. Or we can try to induce superconductivity in a topological material, which has some special spin texture in the states. This is in our work, this topological material can be topological insulators and also topological Dirac semi-metals. And these are the main types of device or experiments that were proposed in the last few decades, 10 years maybe. And we are mainly focusing on the superconducting device, namely making Josephson junctions based on different topological material. I think we had also the same, even the same figures as Alexander. We do use the property of this backscattering protection in the topological states. That is the consequence of spin momentum locking in such states. And usually we present this in a 2D surface state of topological insulator. But also this spin momentum locking can be extended to different dimensions. So for 3D and 1D, it can also have this spin momentum locking. And this gives us a very important consequence in superconducting devices. So once we have such topological material, we are going to induce superconductivity by means of proximity effects. And here, this way to do it is by putting two superconductors on top of this material and very close to each other. At the interface, we will have this Andrews reflections that an electron can be reflected as a whole, or the whole reflected as an electron. And during this trajectory, if the phase can have constructive interference, then they will form a bond state, which we call Andrews bond state. And these bond states can carry the superconducting supercurrent, we call this zero resistance state. And there are different situations for the Josephson devices. With a normal, they say, non-topological material in between, we can have such Andrews bond states like this in a one-dimensional situation. So the states can change as function of a phase difference between the two between the two electrodes. And for a perfect transmission, well, we will have a gapless states, but the states are not protected. So if we change the phase difference, it will still follow the lower branch, forming a 2-pi periodic state. And if we have a finite transmission, then the gap will be opened at the phase pi, and still the state is 2-pi periodic. However, if we have a topological material in the middle, due to this backscattering protection, the states become gapless again, and each of these momentum states becomes protected, and they can follow, if we change the phase difference, they can follow a single color branch and eventually forming 4-pi periodic state. So this periodicity I'm talking about is basically a current phase relation. And in Josephson junction, we can simplify this relation by a sinusoidal function. But of course, in a real situation, this current phase relation can be much more complicated. I will discuss later. But first, we can just discuss the periodicity due to this periodic current phase relation. And if we irradiate this sample, the junction, with a high frequency signal, and due to this inverse AC Josephson effect, the DC component in the IV curves it becomes quantized. So for 2-pi periodic situation, this voltage becomes quantized at every HF over 2E steps, given by this integer n. If we have a 4-pi periodic state, and this quantization becomes double size. So instead of having, we call all numbers Shapiro steps, we will have only even number Shapiro steps in a 4-pi periodic state. So this high frequency measurement, namely this Shapiro steps, can distinguish the periodicity in a Josephson junction. So that's somehow we can measure our samples to see whether they have this zero Majorana mode, their energy Majorana mode. So here I'm first show you the results from the bismuth antimony sample. So that is a 3D direct semi-metal Alexander just introduced, and this is the sample. The blue lines are the superconductor leads, and this is what we measured with RF power, RF signal. So we can clearly see the Shapiro steps, and the first step was missing, and this can be seen also by checking the pinning numbers. So they basically counting the size of the step, and also this color map, which indicating the existence of the step as function of the power of RF signal. So it's quite clear the first step was missing, and this is a little bit different than we just explained, because all the higher order steps are present, and these only the first odd number step is missing, and this is due to the fact since we have a finite size sample, they will have a multiple transport modes, and the 4-pi modes can only be contributed by these perpendicular modes. So only the one which is normal to the interface contributes to the 4-pi periodic modes, and the other transport modes just gives other trivial states. So this is a mixture of 4-pi and 2-pi states, and therefore usually the higher order steps just only show in the 4-pi property, 2-pi properties. And of course, we can also check this mission step in different frequencies, and we can see at the higher frequencies, this 2-pi mode is completely recovered, and this is giving us some indication or the estimation for the 4-pi periodic currents contribution in the total current. So from the frequency at which this mission step is completely recovered, we define this maximum of 4-pi periodic component, and we estimate this to be about 20% of the total current. And the frequency dependence of this missing step is just increased with frequency. So this dots here means the ratio between the first step size and the second. So it becomes larger and larger in as a function of frequency. That means by increasing the frequency, we will get more and more first steps. And this is argument that we use to explain why this cannot be the Landau-Zener transition, which also might induce some 4-pi periodic states. Okay, this is basically the same idea I just said. So we can define such critical currents and estimate the percentage in the system. And we also say the percentage of the 4-pi periodic mode could give visibility of this mission, of this mission step. And if the percentage of the 4-pi periodic mode is too small, then this becomes invisible within this RF measurement. And similar results has been observed also in the 3D topological insulator samples. So this is the one with collaboration with Jülich Center. We have very nice in-situ deposition techniques to generate high transparency samples. And this is the one we made in Twente using the high quality single crystal of business BSTS crystal. So both of them show in the mission step in RF measurement. And now I'm going to discuss something very interesting in this 3D Dirac semi-metal, that is a giant Zeeman effect. So we know in bismuth, also we believe in a bismuth antimony sample, the band structure are quite similar, that we have a hole pocket at the gamma point, and at the L point we have three very elongated electron pockets. And this elongated pocket, we can describe it with a linear dispersion, so the Dirac equation. And we know if we apply a magnetic field in this material, it will just simply shift the band structure along the direction of the magnetic field. So together it looks like this with this equation. And it basically means by applying a magnetic field, we can shift the momentum of the pocket. So the pocket is shifted along the magnetic field, and if we apply the field in the Josephson junction, and that means we can have a finite momentum pairing in the system. And this shifted the finite momentum would generate a phase, extra phase in the superconducting correlations. And then there's a condition that this shift is related to the distance between two electrodes. So if this phase becomes pi, then we will have oscillation in the supercurrents. And this is what we...
Оно автоматически заходит как... Оно почему-то автоматически заходит.
Okay. I cannot hear you, Alexander, Sasha. I guess I just continue, right?
Yes, please continue. It was some person speaking. I muted him. Okay, please continue.
Okay.
Yes.
So yeah, I was saying the momentum, the finite momentum we induced by the magnetic field can be expressed in like this. So it's related to the G factor and also, of course, your Fermi velocity. And we know that in bismuth, this along the elongated direction, the G factor can be very huge. So that's what we got from the literature. And also we observe this oscillation of supercurrents as function of parallel magnetic fields. So the configuration is like this. The field is along the direction of the current. So if we use this oscillating condition, then we can deduce this effective coherence length in the system. So once, basically every node means the phase equal to pi. And of course, once this crosses node, the system, according to this model, then should have a transition from 0 to pi and alternatively change. And in this SFS oscillation model, we know this effective length can give us two parameters, which one beside this K factor, another imaginary part gives the periodicity in 0 pi transitions. And for giant Zeeman effects here, we might, in the intermediate region, comparing to the two situations here. So for the clean limits, there's only oscillations, or it's periodic in B, but there's no decay. And in the diffusive limit, we have periodic in square root of B. So in our case, we are in the intermediate region, which is periodic in B fields and have an exponential decay of the amplitudes. And so now I'm going to talk about the current phase relation, especially by measuring the current phase relation, we can also determine whether we have this 0 pi transition. So that was the motivation to do that at the first place. But also, we measure this the Shapiro steps, the missing first step, and we are interested in the nature of this transport of the junction. So it is favorable if we have a ballistic junctions. And in that case, we, in a single junction, we also measure the temperature dependence of the critical current. And using the Ehrenberg equations, we can fit it quite well which gives us quite high transparency and a long long junction limit. So it seems like we have ballistic junctions, and which also demonstrate some zero pi transition in magnetic fields. So now we are going to measure the current phase relation and try to investigate these properties. So here's just some small summary about current phase relation properties. If we are in a tunneling regime, we should have this almost perfect sinusoidal shape current phase relation. And this can also be affected by the transmissions of the modes. And if we have a short junction, and this is the expression for this current phase relation, and by changing the transmissions, we see this current phase relation coming from a non-sinusoidal gradually back to sinusoidal type current phase relation. So if you have very high transmission, then you have this very deep change at the phase 2 pi. And otherwise, you would just follow the sinusoidal shape. And in the long ballistic junctions, interestingly, this current phase relation becomes linear in phase difference. So it's showing this sawtooth shape current phase relation. And so in our case, we are interested in to see whether this current phase relation follows one of these two special current phase relationship. Okay. So that's what the sample. This is the schematic drawing of the sample. We have this Josephson junction on the based on the Josephson antimony, and we also have a niobium constriction at the end of the a little bit far away from the junction, and this constriction gives a much larger critical current than the actual critical current in the sample. So in that case, this form a squid device, but it is asymmetric. So this critical current is much larger than the critical current in a sample. And this is what we measured. So after some background subtraction, we got a quite tilted and a linear shape of critical current that very much align with these situations. So we can say we have a long ballistic junction, and also showing a very nice fitting to the theoretical calculations. So actually this paper is published. I forgot to change this. And this is the right reference. So in the, we measure this current phase relation. So we're very happy. And then we change the temperature. We can measure the amplitude, basically gives the critical current in the junction. Then by changing the temperature, we can extract this amplitude, which is the red dot here. And we fit it with, again, these Ehrenberg equations. And just by fitting this temperature dependence, we can automatically generate the current phase at different temperatures. And now I just put it, I just fit this one, and then I just plot the current phase that I calculated, and it fits almost perfectly to all our data. So this we can say quite safely we have a long ballistic junction. And now I just showing this 2D maps that I first changed the perpendicular field, which tune in a very small range, so tune the phase difference that we saw here. So that's the phase is tuned by the perpendicular field here. And then I varied the field along the parallel direction, so along the current. And you can see how this current phase relation evolutes with the parallel field. So you can see this blue and red region just alternate between them. And each block is phase pi. And if we look at this profile cut, you can see the maximum and the peak just alternating between them. So that basically means we do observe a 0 pi transition in our junction as function of a parallel field. And if we fit this amplitude from the data, then we can extract these two components we just discussed before. Okay, and now I'm going to discuss another material. It's also a 3D direct semi-metal, but it has some special properties. This is called gadolinium arsenide. So first, this material has an inversion protected Dirac cone to have two cones, two Dirac cones.
Right.
And so one property of this wire cones, I don't know if you know this wire semi-metal. So it's a 2D Dirac semi-metal can be seen as a pair of wire cones. And some special property of the wire points is they always come in pairs. And then the Berry phase calculated there can be estimated to be a positive and negative value. And this basically gives us a Berry phase difference. And so to equilibrium this, get equilibrium between these two Berry phase, we always need a connection between the two. That's the intersection with the Fermi energy on the Fermi surfaces. So there's always a 2D surface state, which we call now the Fermi arc, which connects to the two wire cones. And these Dirac cones, it just sometimes can be seen simply as a pair of wire cones. And in cadmium arsenide, we have two Dirac cones. So basically they can have another pair of wire cones and then complete the circle of such Fermi arcs. So this photo picture can be somehow drawn like this. You have two, they say, generate wire cones at the Dirac point, and then they have closed Fermi arcs on top and bottom surface. So this interesting property has been proved by thickness-dependent quantum Hall effects. Okay, so and one more property is that this material has very low carrier density, so we can tune the Fermi energy by a gate. And now, from previous results, we know that the multiple transport modes will only give this trivial anti-bond states, which diminish or reduce the visibility of our 4-pi periodic mode. So the natural idea is to reduce the size of the bulk and leave only few modes or even one mode in the junction. So here we investigate this nanowire, the cadmium arsenide nanowire sample, and we made it into a Josephson junction. And indeed, now we measure the Shapiro steps, and we see a multiple even steps. So not only one, but the third and the fifth also disappeared. And we can carefully tune this with a gate. So this property is strongly related to the visibility is strongly related to the Fermi energy. So this work is in collaboration with Beijing University. And in such structure, because the size of the nanowire is small, so we have only few modes in junctions. We even see the oscillation, the interferences of the few modes transports. And this also has been observed in the nanoplates. So they intrinsically have much more modes, but you can still see some interferences when you apply the parallel field. So the clearance length is very, very long in such system. And also the surface states indeed play an important role. So now let's move to our final topics, and also a very important new physical phase in condensed matter. So here we have this quasi 1D transport in the nanowires, but ideally we want to have some pure 1D states and with robust bulk system, because if you continue to reduce the size of the nanowire, you might decrease the quality of the nanowire. So that could be an option, but maybe not the best. And on the other hand, there are a new topological phase has been observed and protected in this field. That's the higher order topological state. So by the name, we can kind of guess what that means. So for the first order, which is the usual topological states, in a 3D system, that's a 2D surface state. And the second order, which is the higher order, that gives you a 1D, one-dimensional hinge state. That's already this 1D channels. And this is what we're talking about in atomic scale. And that's basically what we want, and ideally for these topological devices. So in this, theoretically, it has been first calculated in the bismuth, and also later in cadmium arsenide as age of the sample. Yeah, just the age of the crystalline. We should have this 1D hinge state. And we want to measure this. The simple idea to measure these states are just using the interference effects of the supercurrents in the magnetic fields. So if you have homogeneous current distribution in your junction, you should observe this Fraunhofer pattern of your critical current. But if you have only or much age channel contributions, then you will only observe these squid-like patterns. So they are quite different, and also both in amplitude and periodicity. And this is what we measure. So in cadmium arsenide nanoplate, we observe this clear periodic oscillations in the critical current. And that basically gives quite solid proof that we do have these age channels in the junction. And interestingly, a few years ago, when I was in Paris, we also measured this squid-like oscillations in this long bismuth nanowire, and we also see this squid-like pattern. And at that time, we didn't know what's the physics exactly behind. But nowadays, we know that this is also the higher order topological state in bismuth. So now we do have a nice platform to do this, to make the devices. And in the future, we can try to improve this material by inducing magnetic gap in the system. Then we'll have a chiral modes as H and no conduction at the bulk. And of course, it's also quite natural if we can reduce the size of the dimensions of the sample and by making thin films. And other alternatives possibilities is using this crystalline topological insulator, which also has a higher order topology. And at the end, we can design these braiding devices and to make a non-abelian statistics in these topological superconducting devices. Thank you. That's it.
Yes, thank you very much. So very nice talk, very clear, I hope so, for everybody. So we have time for questions. So please, maybe somebody wants to ask for some more details. Okay, don't see any questions so far. Okay. Maybe I can ask just a very general question. What do you think is the most promising direction to go further? Is it a nanowire or 3D or 1D? What do you think? What is your opinion?
I think no, I don't think a nanowire is a promising direction. It's nice to do a proof of concept. This is nice quality, but you can imagine if you want to do braiding, you do need something in 2D, right? So to grow such thing with nanowire is too difficult, I think. People try to do this in 2D gas, also this semiconductor-based 2D gas, and or we can do this. And they have a natural age states, so you can shape it as much as you want.
Okay, but on the other hand, of course, we can argue that in 2D, topological protection is not so perfect anymore. Yeah, so 1D is maybe better for view of really spin momentum lock in 2D. We may have Majorana states only for certain directions and so on. So maybe we have to do something in 2D platform, but making it okay.
Yeah, so that's here makes it
yeah?
quite promising now because it's topologically protected 1D state. So you do being immune to many of these perturbations.
Okay. Yes. So more questions? Okay. If not, then thank you, Chan, and I will. Then we close this talk. And so we meet again in 20 minutes, exactly at 15 o'clock our time. Will be given by Professor Lukanchuk about ferroelectrics, topology in ferroelectrics. It will be very interesting. Please, everybody is welcome. And still two talks today. One of Professor Lukanchuk and another from Professor Vinokur. So two nice presentations. Okay.
Okay. Thank you.
Okay. Goodbye.
Bye.
Yes, as I mentioned, the full recording will be available on the website of the school. You will have a link soon. Okay, so please start. So.
So, hello everybody. I think we have some problem possibly with echo. Yeah. Uh-huh. Hello. Yeah, possibly now it's more or less okay. Slideshow. Uh-huh. Yeah. So, hello everybody. I will speak of the subject that from the first point of view can be a little bit out of the subject of SPINTECH, but actually not. And I will speak about ferroelectrics, which possibly the material for some of the participants can be new or not quite know. But actually, I will speak about the same subject, which is the subject of the school. The work of the physicist actually is divided by of the people who work with electrons and the people who work with structure, and there's some gap between them. So I will try to fill this gap and show that the same effort to produce the new materials for the future calculations are can be solved by the synergy of both approaches. So I will be speaking of the very fundamental thing of topology of ferroelectrics, and at the same time I will show how these new discoveries in topology of ferroelectrics can be applied exactly for the purposes of the future computers. So I need to tell that my talk is done in the frame of the European Marie Curie Rice action. And actually, this action is complementary to the action of SPINTECH. And I would like just, before starting my talk about science, I would like just to tell something about actually the objective, exactly to demonstrate how close we are. And actually, we now consider as both of our European project as some kind of synergy or project clustering, which is very required by Europe, and I think which is give much more audience and much more synergy in understanding of the phenomenon. So we are looking, so our project is Melonis for memoristic and multiferroic materials for logic units in nanoelectronics. So you already see that we are doing almost the same, but with the different materials. And our objective, again, it's very in line with the objective of SPINTECH, develop the innovative material platform to emulate self-organization of neural connections and overcome the tyranny of the deterministic binary logic to make a machine think like a human. So the member of our network by University Jules Verne, France, Argentinian very large node CONICET. It's actually, it includes almost of Argentinian research system, University of Zaragoza, small and medium enterprise nanotech in Kiev, University of Groningen, and also the Russian university, which we are now integrated in our network, is South Federal University of Rostov-on-Don. Just I would like to show, before going really to scientific part, our network. So you see it as a transatlantic network that joins together European countries and countries of South America. Actually, it's another type of action, of Marie Curie action, which is called RISE. So it exactly the action of working integration of the set countries. And we are very happy to have such very strong partner from Argentina. And I hope now with collaboration with SPINTECH network, we can really extend our geography and possibly even do some very nice school in the very nice places outside of the Europe in South America. So now let me go to the subject, to my talk. And as I told before, the subject can be somehow out of, let's say, some not general knowledge, but deep physical knowledge. I would like to just recall are the ferroelectrics and what are the important functionalities of ferroelectrics. So in principle, ferroelectric, again, it obtains its functionality because of the structure phase transition. When, for instance, this is a typical example of perovskite ferroelectric, when the central ion is displaced by due to the phase transition from the central position, and such a way the material acquires a new functionality with polarization. Then polarization is like magnetization, very, very roughly in magnetic system. We have the hysteresis, and because of this, of course, this hysteresis allows us to do the memory, which is actually very similar to the situation in magnetic system. So this is again almost the same formal physics. The level of formal description is based on the Kinzburg-Landau equation with at least two well potential, and with the temperature dependence of the order parameter, like in usual phase transition. So, and as it was also told in the morning. Sorry. Okay, yeah, okay, yes, of course, yes, yeah, very good. So, and as it was discussed in principle in the morning, our computers is out of the limit. We are close to so-called Moore. So Moore law possibly is very, very difficult to follow because of the very strong overheating of the computing system. A new quality way should be designed to overcome this so-called Boltzmann tyranny of the overheating of the computer circuits. So I will discuss two approaches, two proposed approaches, which is based on the non-binary logic and normal computers, based on topological structure of ferroelectrics, and also on the effect of the negative capacitors that can be used for the low dissipation electronics. So again, we have ferroelectric polarization up, polarization down, so it can be used as a memory system. Because of the reasons that I will tell later, there is some delay of development of the ferroelectric memory, although several chips exist at the market. So this is, I mean, some another publicity from Fujitsu also produced some electronic chips with ferroelectric inside. However, there is some delay. You see, this is very old transparent, dated by 2005. In 2005, they told that in 2010 we shall have 3D ferroelectric memory, which is of course not the case. So there are some objective, but mostly subjective reason why there is some delay. I will tell about this a little bit. So now, just let me go to some first ideas that is coming from ferroelectric is to construct the multi-level logic based on the ferroelectric. So it just for some general remarks that our computer are binaries, they are based on the yes or no operation. Although mathematicians, they suggested another types of the computations many years ago. For instance, ternary logic, it seems it's better because it simulates the human thinking much better. And there is a crucial difference between binary and ternary, because binary is deterministic. You have either yes or no. Already ternary logic, it contains also maybe, which is typical human quality, and which can simulate the processes in the human society much better. And of course, quaternary logic that with yes or no contains yes, yes, no, neither yes or no. So there are a number of levels in the logic. It's not just mechanical increasing. It contains some new categories that are not that are very difficult accessible for the usual binary logic. And it seems such type of I will tell now about the memory. The principal idea is very simple. So, and it's easy realizable in ferroelectrics, for instance, in magnetic system with spin down, spin up, spin down, because here the polarization, according to the symmetry of the system, the polarization vector also can have not two directions, but 3, 4, and so on, according to the anisotropy axis, number of anisotropy axes in ferroelectrics. So the first coming idea that it's very good to realize such a system. And as we show before, in principle, in very, very classical ferroelectric materials, lead titanite, we can have up to 4 non-equivalent direction, and at the phase diagram, we can realize very, very different types of the switching. So, roughly summarizing what can be done, we understood that if we are going to the logic that contain more than 2 elements, we can realize a lot of different types of the switching or of the access to these elements. And the hysteresis loops can be very, very different. So you see, in principle, you have, for instance, 4 levels, but you have very, very different types of the access. You can go from -1 to 2, from 2 to +2 to the -2, and so on. And what is shown here, it is all of the possible, just from the point of view of combinatoric analysis, all the possible hysteresis loops that can be realized for the 2 or 3 level logic. And very interesting that even in such traditional materials like lead titanite, so all of the scalars, so this is what is shown here is the possibilities of obtain the hysteresis loop as function of the applied strain, strain by the substrate, for instance. And really, we can, by strain, we can tune very, very different logic hysteresis. So actually, it means that we have not only multi-level logic, we have multi-level logic with tunable architecture. And this is, for us, is one of the possibilities of the development of future logic element for computer. You can not only tune the number of levels, but you can also tune the different topology of access of the different levels. So such a way what was shown at the figure, we just schematize this by this round circles, which +1, -1, +2, -2 different levels or different branches in the hysteresis loop. And we have shown that there are different logical possibilities to switch between all of these levels. So this is non-Aristotelian logic, although, frankly speaking, Aristotle was the first who told that there are different logics. And this is one of the ways, as you see, how we can increase the capacity of computers, but also how we can improve, but develop, make some progress in the computer architecture just by realizing this type of the switching. However, it was just some preliminary talk because I will mostly speak about the ferroelectric on nanoscales. And if we are going to nanoscales, we have shown there are plenty of very, very different states in ferroelectrics. By the way, this is also case in some magnetic materials. And we can realize the different logical states, not only due to the different symmetry direction of the polarization, but also due to very different topological configuration of the topological defects inside of ferroelectrics. So now I will put the main highlight on the discussion of the topological defects in ferroelectrics that actually also contains the universe of the physics. Actually, I think it is only now the people start to recognize that when we are going in ferroelectric from bulk ferroelectric to nanoscale, we obtain completely new materials with completely new properties that are very, very different from that new physics from that was discussed before. So there are, well, this is what is shown is different technologies of different structures. Now let's look what happened inside. So what is shown here is not the picture of Matthias or some another painter. This is some pictures taken from recent publication in the high-level journal of the discovery of the different topological defects inside of the ferroelectric. So these topological defects or topological structures, more correctly, they are formed by the vector field of the polarization vector. This looks like really very, very nice and like fine arts. But actually, I was promised not to give the formulas, but I will show just only one formula which describe all of this structure. And for me, as for theoreticians, this formula has much colors than the picture before, because really it contains university, the universe, and this universe is inside of the parameters. Roughly speaking, here we have the Ginzburg-Landau equation. We have the Ginzburg-Landau equation, the first line for the polarization formation. We have the gradient terms, and after what is important and what make ferroelectrics possibly different from all of other functional materials, that we have the coupling with long-range electrostatic field by virtue of the polarization, or with elastic field. Elasticity here is also very important by virtue of coupling of polarization with elastic field. But this was my last transparency with the formula, but everything is there. So now let's look what can be done. And my principal claim that ferroelectric is a topological materials, and possibly it even much more topological than some another materials that are called topological materials, because really it contains intrinsic reason for topology. This is the long-range Coulomb interaction that is interacting with the polarization. So I just showed several funny structures that we obtained, and you see how rich is evolved. But next, let's say 20 minutes of my talk will be just devoted to discussion of this structure. And several real structure was discovered, I think, describes in such detail, possibly for the first time. So, but let's now make some step back and discuss the origin, why it is topological, and what is new we have at the nanoscale. So the principal phenomena is the coupling of polarization with electric fields. So electrostatic forces coupled with Ginzburg-Landau equation. So if we are looking just for the slab of ferroelectric, we have the imagine that we have very simple case. We have the monodomain ferroelectric material. In this case, polarization will terminate at the surface of the sample, and according to electrostatic, we shall have the depolarization charges that are formed at the end. So the principal formula that we have here is the charge is a divergence of P, and these charges that will be formed at the polarization termination at the surfaces, naturally they will produce the electric field. So one more functionalities in this story, and this electrostatic energy costs a lot of energy. If we are just doing very simple estimations, we immediately obtain that energy of this electric field will be much higher, can be several orders of magnitude, than the energy of condensation of polarization. So in this case, ferroelectric cannot exist. Well, this paradox, of course, scientists, they talk about this paradox already many years ago. But for bulk materials, it was less relevant, because in bulk materials, you always have the screening charges that come in from somehow from the air, or you have some impurities. And actually, in bulk materials, this depolarization paradox is much less relevant. But if you're going to nanoscale, this depolarization effect becomes of the primary importance. And This is what making the difference between the ferroelectric nanomaterials and ferroelectric at the macro scale. Actually, as I told, the people put attention on this depolarization paradox many years ago, and the idea of ferroelectric memory is not a new one. And here is some examples. So, and this problem, I mean, is the professional world of the electronic engineers was called the absence of scalability, because what was told that below certain critical thickness, the ferroelectric polar state is thermodynamically unstable. And for TGS is kind of ferroelectric. The critical thickness is calculated to be 0.5 micron. So the people who were working battery at Silverman, who were working at the time in IBM laboratories, they clearly stated, it was theoreticians, that one cannot do ferroelectricity not only in nanoscale, but even in the macro scale. After this, IBM, they believe to these two theoretical guys, so close all of the research in ferroelectrics, and after this, ferroelectrics became less popular in the world as with respect to magnetic, their magnetic homologues. But actually, it's, we theoreticians sometimes make some mistakes. And the mistake was, no, I would not like to tell that it was a mistake. They just did not know well the history, because already Landau and Lifshitz in 35, they perfectly considered such a situation. They considered it for ferromagnets, but the same, even stronger, will be for ferroelectrics. And they treated the problem, and they told that no, we shall obtain new quality, but ferroelectricity will not use it. After this was described in Kittel 46, it was called Kittel domains, and we forgot until our time. And the people just from ferroelectric, from the laboratories, they did not know the basics really of theoretical courses, or the course of theoretical. Because this problem is Landau-Lifshitz volume 8. So what really happens, it was our calculation in 2005, that the system really will split into the domains to avoid this depolarization paradox. And what really happens, you see, if system is split on the domains, the charge, depolarization charge at the surface will alternate. We shall have plus minus, plus minus, plus minus. And because of this, the charge will not penetrate anymore in the bulk. The electric field will not penetrate anymore in the bulk. It will be concentrated in the vicinity of the ferroelectric. Because of this, the depolarization energy will be drastically reduced. The price which we pay for this is the energy of the domain walls. And of course, one should calculate the balance between the period of domain structure and the depolarization energy. But as what showed Landau-Lifshitz for magnetic, and also this our calculation for ferroelectric, the system, the thin films, superlattices, heterostructures should absolutely split on the domains. Actually, this was shown experimentally hereafter. Now this structure is called mostly the vortices as alternative vortices as domains, but the theory of first introduced by Landau-Lifshitz works perfectly. And this is the electrostatic forces, new quality that is acting at the nanoscale that produce such a nice structure. So here is the result of experiment that actually confirms this calculation of 2000. But now my objective is to go further, because now many people already believe, although it was very, very difficult to convince people 10 years ago about this possibility of this vortices, but now I think community, ferroelectric community already believe, and it creates some question of the discovery or of the study of the so-called vortices in the two-dimensional films. But we shall go further, and we shall consider more general ideas concerning the topological structures in ferroelectrics. And I would like to tell, I promise to not write formula, but I'm sorry, I wrote one more formula. There's a formula that the system is trying to avoid the polarization charge. And the formula is if P equal to 0. So my claim is as follows. This formula is enough, well, under certain another, of course, suggestion, is enough. It completely changed all of this complicated Landau-Lifshitz published studies. Of course, one should be very careful. But what is the origin and what gives us the new physics of our electricity is the absence of the depolarization charges. The system trying to arrange the fields of polarization lines such a way to avoid depolarization charges. In principle, this formula should qualitatively explain all of the physics of paraelectrics. Of course, one should possibly perturbated term, but in principle, all of the physics is already there. And this is something that I would call it déjà vu, because we well known that the subject of the divergence was well described already in hydrodynamics. Can map now texture of polarization should more or less have the same physics as the flux of the special So, and we should try to problem, which unless the very, very simple problem, is also very, very complicated. So what I show here is the result of the simulation done by us for ferroelectric at nanoscale. It was artificially introduced some impurities and so on. And you see this is simple formula results. It's a very, very difficult, very, very complicated and very sophisticated knotted structure. So very rich physics inside of very, very small formula. The color of the color of this picture is just the modulus of polarization. So larger, smaller, and the red is just the calculation measure. So and here you see now, and really what I show is something very complicated. It's our objective to make some general description of the textures. But first of all, we stopped in the most simple case of spherical nanoparticles. And actually, it was believed that spherical nanoparticle, they should have the vortex texture of polarization exactly to avoid this absence of the depolarization charge. We did numerical simulations based on this complicated Ginsburg-Landau equations, of course. We also obtained this vortex structure, which is shown at the upper panel. But at the given moment, we try to trace the field lines for this vector field. And we thought, wow, because what we obtained the very interesting texture that is shown below. This texture, actually, it was not a vortex. It was a field line knotted around the system of the nested torus. Actually, this structure, it is already was discussed by mathematicians, and it was discussed also in several analyses, even in magnetism. It was never really observed experimentally, and the structure is called Hopfion. Hop was a mathematician who in 30s is genius who predicted such type of the structure. So it was really, and I mean, during 5 minutes, we just changed the button in the simulation program, and we discovered a very, very rich world inside of the ferroelectric nanoparticle. So why Hopfion is formed? So imagine, again, let's discuss the story with the depolarization fields. So in figure A is shown the primitive idea of a monodomain sample with uniform polarization. Of course, we already know that in this case, polarization will terminate at the surface, and the system will be unstable, and this instability will produce the screw of the polarization. So the next idea, okay, let's do vortex. Vortex is fine structure because divergence of vortex equal to 0. We have no charges inside. But if it's vortex, we have only one small problem because vortex contains vortex core. And vortex core costs the energy. So the people, especially who are doing liquid crystals, they know that this problem, nature usually trying to avoid this problem by producing the escape of the vector field inside of the vortex core in the set direction, as shown in C. But in this case, if we produce the screw-like escape of polarization in the set direction, we shall immediately obtain the depolarization charges at the pole of our sphere. And the system, again, it can avoid these charges when it produces a counterflux of the polarization which was at the center of the vortex core, counterflux at the walls of the sphere. Such a way, Hopwork is formed. And it was really quite lucky that we discovered it. Actually, as I told you, although hydrodynamic exists, really topology of hydrodynamic also is somehow terra incognita. And people were working mostly on the solution of the Bernoulli or Navier-Stokes, different type of equation, rather than to look for the great topological ideas that are beyond. And Vladimir Arnold was genius, and he really, at the last year, well, he was working all of the life on the topology in hydrodynamics, and he created some ideas how the topology of the incompressible liquid is working. And in his last book, we discovered the following, that the region of flow can be incompressible flow of the liquid can be partitioned into finite number of cells. Some of cells fibrate into tori invariant under the flow, and those fibrate into surfaces invariant under the flow, deformated to the annulus. This is the vortex. On each of these stories, the flow lines are either all closed or all dense, and on each annulus, all flow lines are closed. So actually, he told that the liquid, the incompressible liquid inside of some volume can be separated on several subspaces, and each of subspaces present as a vortex or the torus. And this is exactly what we discovered in the nanoparticles. So you see, well, it's by the color, show different types of the torus. And sometimes, for instance, from at the left, we have vortex. It's also depends on the parameters of the at the left we have vortex and torus. At the mostly at the right. At the left we have torus inside of the vortex. At the B we have only the system of nested torus. And all of this rich structure, it does depend on the it does depend on the coefficients on the materials properties of the system. Even more interesting the behavior of such structure in the electric field, but it will be the better at this point that I will show this as animation. So let me find my animation. So the movie shows how the system is developed when you switch electric field. First of all, in the electric field directed up, the system is almost polarized, so we have just spiral, but spiral gives us the polarization of electric field in some direction. So what is shown here is two examples of the field lines. Now we change the field, and field goes close to zero. At the given moment, you see we have creation, let's say, of baby. We have creation of the torus inside of the spiral vector field. So we have topological phase transition it's a field. That's why I'm calling ferroelectric as topological materials. Up now, all of the spirals are disappears, and we have the system of nested torus. At the given moment, one of these nested torus is broken up. If we have the Hopfion inside of the torus, and finally now the electric field is directed in the opposite direction, and now we have the spiral of the vector of the polarization field directed in the opposite direction. So in such type of the switching of the polarization, we had at least 3 topological transitions that are described different topological entities inside of the cells. Yeah. Time scale. So I would expect it can be even picosecond, because everything in ferroelectric is very, very quick. Now let's go to continuation talk. Another thing which are people more known, mostly people known in magnetic materials. This is skyrmion, and skyrmion also can exist in ferroelectrics. But if we produce the ferroelectrics in the form of nanodot, here what skyrmion is, just skyrmion is a fontaine-like distribution of the fontaine-like distribution of the polarization. We have the polarization directed up at the center of nanodot. We have polarization directed down at the border of nanodot, and we have the slowing rotation of polarization. So in such case of three-dimensional polarization, three-dimensional rotation of polarization, also the depolarization field can be minimal and divergence E inside equal to 0. What is interesting, we can form 4 types of these skyrmions, and these 4 types can be just graphically presented as a hand. So first of all, skyrmion has chirality, and second, second property, it has some direction in the center. So it just like can be like the pictogram of the direction of the right and left hands. So this is nanodot that in principle technologically, well, this is 2 different technologies, because there are very good technologies to produce nanodots, and there are good technologies to produce nanoparticles. These different technologies, and now I'm discussing nanodots. Nanodot can be produced by some kind of lithography, and let me now again discuss the stress again that these objects, both skyrmion and Hopfion, they have chirality. And for me, this is the unique example when the chirality is formed in the non-chiral system. You see, chirality is something very, very new, and we have the chiral molecules. Our life is chiral. But I don't know other examples in which chirality can be just formed as a spontaneous breaking of the symmetry. Possibly exists, but just by my knowledge not. But here is unique system, because actually here chirality can be produced due to spontaneous symmetry break. Moreover, we have shown that clever protocol of field switching, field variation, can switch between different chiralities. So we can use a tunable chirality of the ferroelectric nanomaterials. We can produce by design left chirality and right chirality, which of course can be very, very important property for different types of optics. We can really realize here the system with the tunable chirality. And again, if we are going to the logic, again we realize the 4-level logic with 4 states that can be switched by electric field. So possibly I will show you again movie how the switching between the different chiral states occurs. So now we have already nanodots, and we switch the field for these nanodots. So when we start from the very beginning, we have just a system. So the point up and down is the direction of polarization. And what we see now is the domain wall between different polarization, which have some in-plane direction. And because it makes a circle, it produces a chirality. So what we did now, we completely polarize the particle and apply the highest electric field. The protocol is shown at the right. Now we start to decrease the electric field, and because of this, we should have some switching from up and down. And this switching from up to down occurs by virtue of formation of the different chiral structures. And now we have no chirality actually now because we have two block walls with up and with different chirality, but at a certain moment we have perfect one chirality. Chirality is shown by the colors, so blue chirality and red chirality, right and left. And now we have the completely chiral structure. Now field is zero, and we have formatted and tuned chiral structure. Now field goes opposite direction, and now the system goes also the polarization try to go to the direction, but also it occurs through the dynamic variation of the polarization and formation of the walls. Look, now we have something like human cell with the mitochondria inside. So we have, I would love to tell, we have even the precursor of some kind of neuromorphic computer, because we can go further. We can just use these different states if we arrive to tune them, and actually we arrive to tune them. We can use also of them not only as 1 and 0 element. We can use as a system, or the like memoristic system with different geometries, and all of this can be tuned by electric field. And so now everything will disappear, and the system will be switched in the opposite direction. So we can tune everything by electric field, and we can actually switch between different type of chirality. And actually, what I think would be the proper device for study of such type of the situation will be ferroelectric nanodot created, for instance, by kind of lithography or beam etching. So such technology is well defined, is well now well elaborated. But what can be an electric field can be switched now by tip of the PFM or FM microscope. But additional elements that can enter to the system, it can be the laser beam. It can, if you are with some kind of internal polarization, they can favorize this or that type of chirality. And the same laser beam also can be used as a tester which type of chirality is formed inside of the nanobeam. So actually, I wanted to speak also about another subject, which is negative capacitance in ferroelectrics, which allows produce the field effective transistor, which exactly is another answer on the quest concerning the Boltzmann tyranny. And at least it's just believe me, please, that negative capacitance is not a perpetuum mobile. It's something that can be well done, and we as theoreticians we can prove that this is not nonsense. But possibly in our next meeting, I will tell about this also funny effect, which is also devoted for the producing the computers of next generation. And at the very end, I would like just to send my collaborators that I just wrote at the very beginning. So this was team from our Melon network. In particular, it was team from the Rostov University who were doing the very perfect simulation and suggestion of experiment, and even they were trying to do some experiment. It's Yuri Tikhonov, especially Anna Zumner, and for Valery Vinokur, with whom also we did all of this theoretical calculation now, and also this supports it. And thank you all of you also for the attention.
Thank you, Igor. So very interesting talk, which is actually really looks like different field, but closely related, in fact, to what was discussed today. This all goes around new ideas on memory and new type of computing. So questions or any remarks? Okay. Yeah, may I ask just also very basic question? What is experimental status now? So you have shown a lot of nice theoretical pictures. How far is actually realization goes?
Yes.
Maybe
So
maybe I missed something.
No.
Is
See,
it is
actually,
as it's realized and proved? Yeah.
I show you only one experimental. It's true.
Yeah.
I show you only one experimental picture. So it was our prediction. It's 2005,
Yes.
and this is experiment that was done 10 years later.
Okay.
So today, so what I told is perfectly doable because we check very carefully, and actually we have expert in our team. We have Anna Razuma, who's expert from the Rostov. They have not such people, but they are perfect expert in such technologies, and we can recommend all the technologies which should be done. But according to our previous experience, we should wait 10 years. So I think experiment will be done in 2030.
Okay, good time to wait.
Although everything is, can be done now.
So, but basically there is no obstacles, let's say,
No, absolutely.
to measure these things.
Absolutely.
It's very stimulating. Okay, good. Any more questions? We still have time for discussion. Okay, since I don't see any questions, so I pause the recording now, and we still have one more lecture today from Professor Vinokur. It will be in 10 minutes. So then please stay online, and there will be a very interesting lecture today by Valery Vinokur about high temperature superconductivity at 4 p.m. our time. Just a moment, I switched on the recording, okay.
Okay, wonderful.
Okay, let's go to the second slide, okay.
Okay, let's go to the second slide. Okay, this is my collaborator, Christina Diamantini and Carla Trugenberger, with whom, okay, we completed this work. And, okay, well, unfortunately, I cannot be in the audience, but I have a view, okay, this is what our modern means of communications can compensate. This is the view which I have from my window in the background. Okay, let's go to the third slide. And I have to, third slide, please. Sasha? Yes, and I have to thank for very fruitful discussions Duncan Haldane and my friends Michael Kostelitz and Tony Leggett, who really, okay, contributed a lot by the, okay, illuminating discussions. Next slide.
Yes.
And this is just the epigraph which we can, okay, read briefly. And let's try to get this new eyes and look at the topics which we knew from our, let's say, scientific kindergarten. Next slide. Sasha, please. And, well, the story which I'm going to talk about started more than 100 years ago with a beautiful discovery of commonly honest superconductivity. At that time, the physics of metal was known pretty well. It was known that resistance in the metals appears due to scattering on something. And this was characterized by drew the formula and scattering time. And resistance of all the metals was, let's say, found to drop with temperature. But then the expectation was that if we go to really low temperature, then all the motions will be frozen and the resistance will grow because relaxation time will go to infinity. Okay, next slide, please. Oh, no, okay. Can you come back and just, okay. Well, okay, but instead of growing resistance, what Kamerlingh Onnes saw, and he recognized immediately, maybe he was annoyed first moment, but what he recognized immediately was the drop of the resistance immediately to zero. And he recognized that this is a new phenomenon, new state of matter, what he saw, and he actually, in his first report, a few days later, the discovery to Royal Society, he called it superconductivity. Okay, let's go. Next slide, please. Oops. No, come back. Come back, Sasha. Yeah. Now, with the advent of quantum mechanics, we are able now to explain where this superconductivity coming in just one line. And using the most fundamental principle of quantum mechanics, uncertainty principle. It was later discovered that if we have superconductor, this superconducting state is characterized by the wave function of the whole state, the order parameter of the state, and this wave function, as it should be in quantum mechanics, is a complex quantity, and therefore it has its amplitude and phase. And then, according to uncertainty principle, the uncertainties in phase and amplitude, which is the number of particles, compete. So if we know the amplitude or number of particles in this, as we know now, Cooper-Pare condensate, we don't know what the phase is. If we define the phase, then we don't know the number of particles precisely. Okay, this is uncertainty principle. Next slide, please. And then from the experiment by Meissner and Oxenfeld, which was done 17 years later, we learned that in the superconductor, the phase is fixed across the sample. Okay, if you can just push, okay, an arrow, yeah. But this fixed phase means that we cannot define or find out what is the number of the particles in the condensate. Okay, next, please. But this means immediately that the condensate should move without scattering and therefore doesn't dissipate energy, because every scattering event would mean that the number of particles could be measured. And therefore we have infinite conductance in a superconductor, and this is actually all the theory of superconductivity as promised, maybe not in one line, but in a couple of lines, but everything is derived from there. The next, okay, the rest in superconductivity are beautiful, but still calculations. Next slide, please. And then, okay, it was the next exciting discovery, which was, okay, it started a new epoch in superconductivity. This was the discovery of the superconductor insulator transition. Why it was so important? Because this discovery was made in a superconducting films. And according to, let's say, to existing dogma, there were not supposed to be any phase transitions in 2 dimensions, but they happened. This, okay, this discovery was done, okay, as a sequence of beautiful breakthroughs. And the first one is done by Alexander Shalnikov many, many years ago. Here, okay, on this slide, he's very young, exactly when he noticed that disorder can reduce transition temperature in superconductors. And basically, well, remarkably, that at that time, he was able to obtain the films as thin as 1 nanometer. We call it nanoscience now. And then, okay, there is highlighted iconic discovery by Goldman, Alan Goldman's group, where this superconductor insulator transition was indeed observed. You see the transition from the superconducting behavior when the resistance goes to 0 to insulating when it goes sort of to infinity as we decrease temperature. And the transition is relatively sharp. And the next move was done by Tatiana Baturina group, who found actually the compound where this transition was extremely sharp. You can see that the difference between first superconducting and first insulating sample, if we go to higher temperature, room temperature was within 5%. And this was the base of the next remarkable discovery. Okay, let's go on. Next slide, please. Matthew Fisher, another remarkable person, came with a beautiful picture of what was going on. So, okay, he realized that the driving parameter is the resistance at room temperature of this transition. And then he realized that in a superconductor, we can talk about the condensate of Cooper pairs, where vortices, whether they appear by fluctuations or because of magnetic field, are pinned. And when we go to insulator at high resistances, we have just the opposite situation. Cooper pairs get localized. Don't ask me how this can happen. At the time, he didn't know this himself, but it was an excellent, okay, guess of genius. But vortices can make something like a condensate. And at the point where the transition occurs, the system should become metallic with the resistance piece, okay, equal exactly to quantum resistance. Tore, can you move it like, okay, back a little bit, because otherwise I cannot see the screen and I cannot see what is going on. Tore, can you move, can you make it that I could back, that I could see the screen?
This
No,
one?
no,
This one?
I don't see the screen. I see you, but I don't see the screen. Okay, yes, okay, next slide, please. Okay, and this is, okay, this is just, okay, magnified data from titanium nitride films. And if we take the first superconducting sample and lower the temperature, we see that the resistance, so in this case, this is the, okay, next please. If we raise temperature more, this dip is increasing. Okay, could you please push next? Yeah, and then if we drop temperature even more, next. Okay, it drops to zero. Actually, the resistance becomes infinite. And this was, okay, the mark of new super insulating state. And now coming back, we can understand using the same uncertainty principle what is happening there. So if we have superconductor where the phase is fixed, we have superconductivity as we just described. But let's see what's going to happen if we managed to pin or to localize Cooper pairs. In this case, we have uncertainty in the number of the Cooper pairs in the condensate, 0. Please, next. Then it means that we have the phase which is uncertain, but then according to Josephson, according to Josephson relation, we have voltage, finite voltage in the sample, but we don't have any current. This means infinite resistance. So we can immediately see that the existence of super insulation immediately follows from the same uncertainty principle. Next, please. And this illustrates beautiful superconductivity duality. So we have Cooper pair condensate in a superconductor side, and we have localized Cooper pairs. And well, actually, for the moment, we don't know what we have there. Next, please. And now we have to take the historical tour for a few moments. Basically, our condensed matter physics, okay, was marked by few what we really call a revolution. Now, okay, we don't remember that, especially young people, but the first revolution occurred when Feynman's diagrams first came to solid state physics. This was, okay, the revolt, which is hard to imagine now. So it was done by several people, and people who are like, okay, of old generation, they remember again this iconic book by Abrikosov, Grikov, and Zalshinsky, by which we all learned this diagrammatic technique. Next, please. The next revolution occurred in 70s. Well, this, okay, young people, students can take it as a homework to find out, okay, whose portraits we have on the slide. This is the people who realized what is called grand synthesis of 70s, when indeed all the methods of the field theory came from high particle physics, from the field theory into condensed matter physics, in particular renormalization group methods. Next, please. And actually it is this great synthesis from, on which we will base. And then another remarkable, revolt came. It was, we can call it topological revolution. It was the discovery by Vadim Berezinsky, who didn't live long enough, unfortunately, to get this Nobel Prize, and then David Taules and Michael Kosterlitz, who discovered the first actually topological transition, which now we call Berezinsky-Kosterlitz-Taules transition. This was a great discovery, and Duncan Haldane contributed a lot into understanding what is going on. This was discovery which put us beyond, let's say, the Landau-Lifshitz paradigm of phase transition. It was found that we can have topological phase transitions in which we don't have other parameter, but we can have something like change of topological symmetry, if we can call it like that. Okay, next please. And actually 12 years before the experiment, this group of people, two of them became my collaborators lately, predicted the existence of super insulation. Next, please. Using this gauge, topological gauge theory, which they applied to very well-known object, Josephson junction array. And now, this was a beautiful discovery, and now we can, stop a little bit and, let's say, examine what we do have there and which was the base. Basically, if we go to very fundamentals, one can say that, there exists, that all the physics which we have is based on the fact that we have long-range electromagnetic forces in nature. And these forces are described beautifully by Maxwell equation. If we go, the upper lines is the traditional, writing for these Maxwell equations. The next lines, show how these Maxwell equations can be written using field theory notations. So they are symmetric. We add the time as one more variable and make everything symmetric. And then we can immediately see that if we are in a vacuum, then we really have full symmetry between electric and magnetic field. But this is not like that. Then we can ask, what happens if we have material? Then we have to introduce magnetic current as well. But if we try to do it, we can immediately see that if we introduce, let's say, magnetic current, which is equivalent to electric current, then we, violate the second Maxwell equations, which tells us that there are no magnetic charges. Next, please. And we can ask ourselves whether it's can you come back for a moment? Whether this whether this duality of full symmetry between electric and the magnetic field complies with quantum theory, and we can immediately see that no, it doesn't. But then stop. Can you come back, Toля? Then we can try and see what new topology can introduce in quantum physics of electromagnetism. And this is what we know from the textbooks. This is called Aronov-Bohm effect. This is a really remarkable phenomenon which shows the significance of quantum mechanics in electromagnetism. We know that, that in order to describe electromagnetic fields really well, we have to introduce potentials, vector potential and scalar potential, which describe fully electric and magnetic field. Then we can ask the question, what happens if we go around the magnetic field, but the magnetic field is organized in a way that the particle which goes around it does not really see it? Will something happen? And the answer is yes, and this is Aronov-Bohm effect. Basically what we know, that if there is vector potential, which sort of like seems to be a physical quantity, and if we go around this hidden magnetic field, which we cannot feel, nevertheless, the wave function of the function requires the phase, and it means that the energy of the system change. And we even calculate, what will be the change in the phase. Next slide, please. This will be exactly the flux which is going to which is going through the loop made by our particle. And based on this observation, we can immediately construct the full theory of superconductor insulator transition using superconductivity superinsulation duality. And what we are going to use is what became the base of the modern physics, and which was introduced by the remarkable person, Emmy Noether, who, no, come back, please. Can you come back to the slide where this, we saw Emmy Noether? So what happened?
No, it's okay.
Back. No, you go forward to the end.
Okay. Here it is.
Okay. Well, yeah, well, okay. So Emmy Noether introduced the fundamental symmetry principle on which all our modern physics, all the physics of 20th century is based. And what we're going to do now, we're going to describe superconductivity, superinsulation duality using these Emmy Noether symmetry principles. And well, actually, okay, let's go ahead because the time is short. Please, next.
Okay, yes.
Yeah. So first, we go to, we can construct our action using this symmetry principle. So the first two lines show the word lines or the currents which are carried by vortices and by Cooper pairs. Just this, this is just the word lines. And then we know, again, from these symmetry principles and fundamentals of the physics, that all interactions should be local because they have, to propagate with the finite velocity. And this means that there is an interaction between local fields, actually, which feel each other, like, for example, in elasticity theory. Nothing is going on instantaneously. Then we introduce the fields which carry these interactions, and we arrive at the action which describes exactly the propagation of the vortices and charges, but also takes into account Aronov-Bohm interaction, quantum mechanical interaction between them. Please, next. And then we, as usual, we have to add the terms which describes the kinetic or just the energies of the fields carried by vortices and charges themselves. And then we arrive at this action. Well, I mean, I'm not going to really exploit this formula, so don't look, I hope it's not quite, I don't know, fearful. But this action actually encodes the whole physics of superconductor insulator transition. Okay, let's go next. And to understand what is going on there, let's try, because we are now equipped with, let's say, quantum mechanics, let's try to understand what is going on if we have just electric and magnetic fields, and see if we can try to recover a rigorous electric magnetic duality. Well, what I can, okay, don't see it quite. Okay, I understand what I have to do. Just give me, please, 1 second. Okay, so what we can see there are, again, our beautiful Maxwell equations. First, and then, if we want to analyze what is going on there, let us try to, okay, to define the, okay, the, let's say, field tensor, which is symmetric. So it's just, okay, sort of complex conjugated to usual electromagnetic tensor which we have. And then let's introduce now, without, okay, thinking hard about the bad consequences, magnetic current again. Then we can construct symmetric Lorentz equation which takes into account both existence of magnetic charges and electric charges. Next slide, please. Let's introduce, just by hand, magnetic charge exactly the same way which we see, okay, the same way we can see electric charges. Again, if we use Gauss theorem, we know that, okay, the full flux through the surface around this charge will be the magnetic charge. Then we immediately have a problem. The first problem is that the charge was never observed. And the second, that the existence of this magnetic charge contradicts Maxwell equation. Let's try to solve these problems. Well, we cannot solve experimental one at the moment, but let's try to solve the problem why we cannot, okay, why these magnetic charges cannot exist in principle. Let's take the magnetic charges. Let's put the electric charge in the field which is created by this magnetic charge, and let this electric charge to travel around it, but not quite around, but just to make a closed trajectory in its vicinity. Then we can immediately calculate what will be the flux going through the solid angle, and this will be exactly the phase acquired by the wave function as a result of this travel. It can be easily calculated. I don't see the next slide. Yes. Well, okay. So look at the left panel. We make a closed, okay, curve, the out travel of our particle. We calculate magnetic flux due to magnetic charge through this, okay, through this surface, and we immediately get, why, Sasha? Guys. Yeah, and we immediately, okay, get the phase which wave function required. Then we can do the next. Actually, we can integrate not through this small surface inside this our loop, but we can use the rest of the sphere. We have to get the same result, but our phase will be different. And this phases, okay, but the wave function should be the same, so we can write this equality concerning the phases which we acquired. And then we immediately arrive what is called Dirac quantization condition. This remarkable relation which was obtained by Paul Dirac and which tells us that the quantum of magnetic charge and quantum of the electric charge are related to each other. And then the minimal magnetic charge which is possible in nature, if they exist, is just equal to the elementary magnetic flux, which we know so well from the vortex physics. And this is the charge of one magnetic monopole, how Dirac called these particles. Next slide, please. Now, how can we still solve the problem that it seems from Maxwell equations that magnetic charges cannot exist? Well, if we not going deep into these formulas, frightening formulas, let's go next. And what these formulas teach us is that if we use vector potential in a very special way, we recover Dirac quantization condition. And next slide, please. And if we realize that we can use these gauge fields, vector potential fields, so that it is singular around one line Dirac string, then the existence of magnetic charges, magnetic monopoles, become really even theoretically possible. Okay, next slide, please. Now one can ask, why do we need, to go into this not heavy but still, mathematical exercise? And why do we need these monopoles? Well, to answer this question, come back, please. Back. Let's recall what is happening in type 2 superconductors when we apply magnetic field. Well, we know pretty well what is happening, and this we will see in a minute in the next slide. As soon as we apply magnetic field penetrates the sample if this type 2 superconductor. Cooper pairs condensate start to go around these magnetic lines and squeeze them into what we call abricosal vortices. Now, what happens if we really have monopoles in our system? Okay, next, please. Okay, and next. If we don't see anything, suppose we live within superconductor, and then we don't have anything outside it, then formation of our vortex will be seen as a result of two monopoles which appear at the edges of our universe, and then Cooper pair condensates squeeze the lines, magnetic lines connecting these monopoles into the vortex. And what happens in a superinsulator? This is a mirror analog. Could you please, just push next. This is a mirror analog in what is happening to superconductor. If we have two charges, plus and minus, carried by Cooper pair and anti-Cooper pair, then we have a condensate of monopoles. They move around these lines exactly the way Cooper pairs were moving around the vortex. And they squeeze electric force lines, which we know so well from our, let's say high school, into electric string. And this electric string has a linear tension, and then it binds Cooper pairs together. And since it binds Cooper pairs together, this is an analog of the magnetic vortex, these charges cannot move anymore. And therefore we have infinite resistance. Please next. So this is what we need these monopoles for. With their help, we can immediately explain where superinsulation comes from. Next slide, please.
Yes, next slide.
Yeah, well, and then we can, let's say, go to the history once again, and we can find out that exactly this picture was proposed in high energy physics, particle physics, by Gerard 't Hooft, who proposed exactly this mechanism for quark confinement in elementary particles. And actually he was the first to invent this term superinsulator, because he said exactly, well, he guessed that this will be exactly the state of matter which binds quarks together. And this is exactly and the phenomenon which describes superinsulation, the dual mirror of superconductivity, is the linear confinement exactly identical mathematically to the quark confinement we have in the particle physics. Please, next slide. And we have to solve only one question now. Whether, next.
Yes, okay, next one. Yes, okay, next one.
Yeah, we can try to discover. Okay, can you push for the next two? We did have a beautiful theory which appeared in 1996, which indeed described the superinsulating state in terms, well, not quite, but we know how to do it now in terms of monopoles. And then the only thing which we have to guess is whether indeed these monopoles appear in a real system. And to do that, we can analyze what is happening in the two-dimensional Josephson junction array. This is a beautiful model system, which can be easily realized experimentally, but at the same time, it can serve as a model system for superconducting fields. And then we can immediately see, and this is illustrated in the right panel, that if we have like Josephson vortex in this Josephson junction array, this vortex, to make this vortex or to remove it, requires some energy. But this energy is logarithmic, growing logarithmically with the distance, and therefore actually the barrier is low. And therefore quantum fluctuations may immediately destroy the vortex in the position it is now, organize quantum tunneling of monopoles, which make it, and this vortex appear in some other place. Therefore, if we really have this Josephson junction array, quantum fluctuations being strong enough can create monopole, anti-monopole plasma exactly the same way we have vortex, anti-vortex plasma, even in the absence of the magnetic field. Okay, please, next slide. So indeed, we do have this monopole plasma because our logarithmic barriers are not high. And using this concept, please, next slide, we can immediately construct the comprehensive theory of superconductor insulator transition. And this allows us to solve, well, one of the grand challenges of condensed matter theory, because in some of the transitions, we didn't go into this, deep, because, deep into the experimental data. Sometimes when we see this superconductor insulator transition, we see intermediate metallic state. And all the people studying this science were telling this, that this is not understood, and it was not understood until very recently, let's say even a year ago, because basically, again, our paradigm or our dogma or orthodoxy of the physics of the electronic system tells us that in 2 dimensions, metals cannot exist. Well, using these monopole concepts, now we know that they can. And this is parameter eta, which exactly tells us the situation when this phase can exist. It means that quantum fluctuations are strong enough to destroy both monopole condensate and Cooper pair condensate. Then this metallic phase appears. And, well, this is quite encouraging because this picture describes exactly all the properties of this boson-metallic phase, which we can see experimentally. And encouraged by that, we can move on, please, next slide, to even more exciting topic. Okay, next, please. yeah, this is to illustrate what I was just telling about. We discovered that this metallic phase is in fact a topological insulator. And next slide, please. Now we can undertake even more ambitious task. We can try to explain the origin of high temperature superconductivity, which is considered now to be one of the major unresolved problem in current condensed matter physics. Please, next slide. And this is the phase diagram of this high temperature superconductivity. And there is a remarkable thing which is called pseudogap state, which appears in the so-called underdoped high temperature superconductors, which has a lot of properties which were measured experimentally very well, but not explained and not understood. And that's why it was considered that this understanding of this pseudogap state, so the state where Cooper pairs seem to exist but not result in superconductivity, can be the key to understanding what this high temperature superconductivity is. So the main properties are the following. There is a magnetoelectric effect in this pseudogap state, which is shown by green, Somehow it disappeared.
I have to get access to Hans, because he's in the waiting room, some people, we go back to your lecture, There are several people who cannot join because I have to give them access. Now it's okay. Now it's okay.
Let's see. Well,
Comfort you, I have seen the talk so far, but on the telephone.
Okay. So now we resume. Valera, please go on.
So this pseudogap phase, which has these beautiful properties, like magnetoelectric effect, nematicity. It means that it behaves in some sense as liquid crystal. It has like one preferred direction in its resistance. Then it shows really strange. The resistance depends as square of temperature. This is the standard Fermi liquid behavior, and it's not clear where did it appear in the pseudogap state, because it seems from the experiment again that there are Cooper pairs which are charge carriers there. Next slide, please. And now we can use one experimental observation, which is considered to be a fundamental experimental observation in high temperature superconductivity, and which is that always, at least in almost all the examples of high temperature superconductivity, this high temperature superconductivity is accompanied by the superconductor to insulator transition. Meaning that if we are in the underdoped state, then the strong interaction between charges localize them into mod insulator, but further doping release electrons and we have transition to superconductivity. And our main assumption, which is actually the main assumption of this science, but which so far didn't go anywhere, that all this phase diagram of high TC superconductors and the physics of high TC superconductors is actually governed by the physics of this superconductor insulated transition and critical behavior quantum critical point. Let's go to the next slide. Now, we can go on in this, let's say, Emmy-Noether spirit once again and see what we can do again with this electric magnetic duality to understand high temperature superconductivity, but first this pseudogap state. So what we have to do? We have the energy and then the action of the electric field written in the first line. This is a, let's say, standard electromagnetic tensor. But then we can immediately notice that by the symmetry consideration, we can add one more term there, which is sort of conjugated to this, our usual electromagnetic tensor. It's marked with the star, which really recovers the electric magnetic duality immediately, and which gives, this is okay, the last two lines on the slide, to a new term in the electromagnetic action. And if we come back to our usual notation, we can see that this new part of the action is exactly magnetoelectric effect, which is observed in a pseudogap state, because this is, okay, because this is the product of electric and the magnetic field. Now, if we look even, okay, more attentively to this formula, we can see that this is the full derivative of the vector potential, and it means that this is sort of the surface effect, and it means it's topological effect. So this magnetoelectric effect is not, okay, it should be there by the symmetry consideration if we have magnetic electric duality, but what more, this is a beautiful topological effect, so we are in the full power to use our gauge topological theory of superconductor insulator transition and apply it to the pseudogap state. And what we can, next slide please. And what we can immediately notice, if we, okay, look attentively at this picture, that this new symmetry term in our action immediately brings us that the current which do exist in the pseudogap state, which has this new term due to symmetry consideration, is actually a mix of charge and monopole currents. And this immediately tells us that the real particles which define the physics of the pseudogap state is not just electric or just magnetic monopoles or electric charges, but that they combine in a new kind of particles, which is known pretty well in high energy physics, which is called dyons. Those are special particles which carry both electric and magnetic charges. And then, after that, we remember that these dyons exist on the topological surfaces at the edges of the system, and some internal edges which we can discuss later if we have time. And dyon condensate forms exactly Fermi liquid because it has fermionic feature as well, thanks to monopole. And then there is no wonder we can immediately show that it indeed provides this T-square, this mysterious T-square behavior. Let's go to the next slide. Then we can see basically that this pseudogap state indeed has all the features. It has nematicity because since they are, they have this dipole electric charge, one direction should be preferable. And then there are Cooper pairs which really carry the charge. And then we can now understand what is the underlying physics of high temperature superconductors. So as an example, I showed a structure on one of the most popular one, it's BISCO. And we know pretty well from the tons of experiments that the superconductivity is carried by these cuprum oxide layers. So this is sort of remarkable two-dimensional / three-dimensional phenomenon, because in terms of the electric properties, this is two-dimensional phenomenon because all these carriers do exist in one plane, cuprum oxide plane. But on the other hand, each unit, elementary unit of this BISCO structure, and it's true about the rest of the superconductors, high TC superconductors, each unit has two cuprum oxide planes, these yellow ones, which are pretty close to each other. Then, by fluctuations, vortices can appear which go from one plane to another. Well, this is like our usual pancake vortices, which we know so well from the physics of layered superconductivity. But then this segment of the vortex can be viewed as formation made by two Dirac monopoles. And then again, since we learned recently that the energy which restricts dissociation of these small vortices is really low, then this, to form dipoles condensate, this magnetic monopole condensate, this vortex can really dissociate. And to have this sort of, in this sense, the system is three-dimensional, and they form this monopole condensate. And therefore, what we really have in this high TC superconductor is the monopole condensate, which coexists with the Cooper pair condensate. And the positive effect of the existence of this monopole condensate is that it makes Cooper pairs a little bit more stronger than they are. And this is the reason where we have this elevated superconductor transition temperature, because Cooper pairs are additionally glued by whatever underlying mechanism is, plus contribution from the monopoles which go around them and, okay, do not allow to fall apart. And that's, okay, since this monopole, okay. And this is the reason or the essence of the existence of ITC superconductivity. Well, I have to stop here. Well, sorry for a little bit of delay. And this is the summary of what this application of field theory and all the, okay, let's go to the next slide, which is a summary. And this is, okay, the summary of what application of this field theory can give us. Sasha, can we go to the next slide? Next slide, please. Okay, so this is the summary. And well, so what do we get? That superconductor insulator transition is inherently quantum phenomenon characterized by full electric magnetic duality. Then combining this electric magnetic duality and quantum physics reveals topological nature of superconductor insulator transition and reveals the existence of monopole condensate, which governs it. Then we can describe all the emerging phases, and this allows us to solve even more exciting problem, to find out what is the origin of high temperature superconductivity. That this is, okay, the same mechanism. We have two condensates of magnetic monopoles, which can make dions, particles which carry both magnetic and electric charge, and which can glue our Cooper pairs, strengthen them, and then lead to elevated superconductor transition temperature. Well, thank you for your attention. Sorry about the delay, and okay, this my technical inconsistency. I stop here. Opening. Thank you for your patience and attention, and we'll open for questions.
Thank you very much, Professor Vinokour, for the very intriguing presentation. A lot of new information which will provoke a long, fruitful discussion also after the finishing of the workshop. But I believe that a lot of questions have participants, me also. Now, can we start the discussion? First question. This is very interesting idea that this parts of the vortices in high TC behave as a monopole. I remember that in your review 2 decades ago wrote about the crossover in vortices in high TC, different phases, 2-dimensional, 3-dimensional, hexatic vortex liquid especially, can we imagine that hexatic vortex liquid consisting of these separated disks or cutted vortices? It is a liquid of monopoles.
It's, well, okay. It's extremely, Tola, okay, thanks a lot for this beautiful question. It's extremely interesting. Well, there were many things which I had to skip or like, okay, keep back because the time is short. And let me tell you, okay, about one which I did skip. You can notice now that what I was talking about actually was the picture which we have in the absence of the magnetic field. Now, these vortices which I was talking about, those were only vortices which appear as a result of fluctuations.
Spontaneous.
Spontaneous vortices, yeah, exactly like vortices which give okay, rise to Brzezinski-Kosterlitz-Staulis transition. Actually, all these transitions which we were talking about, they are either real Brzezinski-Kosterlitz-Staulis transition or quantum Kosterlitz-Staulis transition. Now, your question is extremely interesting because the next question is exactly what is going to happen if we do have finite magnetic field. Then, okay, our usual knowledge about what is happening in the presence of finite magnetic field should somehow be combined together with this fluctuation of physics of these fluctuating vortices, which I was, okay, talking about today. And well, yes, I think that these monopoles indeed contribute, contribute a lot into this hexatic phase physics. And this has to be taken into account indeed. And we really started, okay, this work. And well, it's not finished. We're in the very beginning of it. But the one immediate thing which I can tell you is the following. You probably know, okay, you probably know from the like, okay, beautiful experiments that if we go to the, let's say, high doping state, what we can see is the resistance in high magnetic fields, which is linear with respect to temperature. And then we know that if we switch on really strong magnetic field, instead of linear resistance, resistance which is linear in temperature, we do have, okay, something, is everything okay?
Yes, we don't see you.
You don't see me? Well, I don't know why, because, well, I pushed all the possible buttons.
Okay,
but we don't see, no problem. Can you hear me at least?
we can perfectly hear you. Okay.
Okay.
Please, we will continue. It is
okay. Then we have at very high magnetic field, we have the linear dependence in magnetic field of the resistance instead. So we kill superconductivity and we see resistance which is linear in magnetic field. And we can explain this linear behavior, linear in magnetic field, in terms of this monopole behavior. So, okay, so you have an excellent question. This is the question which we have to resolve, and and
you can refer to certain slide. Yes, maybe.
Yeah.
This slide. Okay.
Yeah. Yes. And we believe that the answer to your question will be positive, and that we really do have, okay, should expect the contribution of this monopole physics into the behavior of the hexatic phase, and well, things like that. But I mean, going a little bit beyond your beautiful question, I would like to say that, okay, this picture, which you can see on the right panels, explains another very recent beautiful observation, which was absolutely puzzling. You probably read this beautiful publication in Nature, where people were investigating actually one monolayer of biscuit. this is extremely, you cannot imagine more two-dimensional structure for high temperature superconductors than that. It's really one unit cell. And remarkably, the transition temperature in hard unit cell appeared to be exactly the same as in the bulk samples. Well, the difference in 3 degrees is not relevant. And our right panel immediately explains this experimental fact, because it tells us that in order to, to observe this superconductivity, we need to have only these 2 cuprum oxide, planes, which are close together. These 2 planes is actually a 3-dimensional structure which ensures all this superconducting behavior. And therefore, exactly as an experiment, even if you have a monolayer, we will see the same high temperature superconducting behavior as in a bulk sample.
Very interesting. Thank you very much. Actually, it provocates a new area of activity. Practically, one can investigate all experimental results with a new vision, yes, with a new idea, and to check the applicability of these new ideas for the our experiments. With what is motion, with what is this transformation, and practically with the more general what is this physics. Thank you very much once again for this very informative lecture. In spite of difficulties, difficulties are present always, but we can manage to struggle with difficulties. One more announcement.
Anatoly, may I ask another question on the talk of Valerie?
Yes. We just started. Started a session with discussion. Please, listener, participants, have you any questions? Hans, have you question? Please.
Yeah. So thank you, Valerie, for the very nice talk. Even though with the technical hiccups, it was well possible to follow it. Your picture of the dyons, as I let's say interpret it, it means that the Cooper pairs have a kind of an angular momentum, like a rotation. Is that a right picture? And does that mean that the electrons have a, let's say, not a collinear K factor, like a K and a K minus, but that there is an angle between the 2?
Oh, it's a beautiful question. And actually, it's, well, Hans, thank you very much for this question. It's a very fundamental one. You just got to the point. The remarkable thing is that dyons, do not have this angular momentum because of the symmetry, but you are absolutely right. If we have this, what is called theta term there, the electrons will immediately require angular momentum, because this picture is adjusted to the, Cooper pairs, not to the electrons. And that's why they, they can exist as a fluctuations, electrons in the pseudogap state, but they cannot exist as an independent carriers. And that's why all the charge carriers and Fermi liquid behavior, and this was measured by, you may know that, this was measured by Ivan Božević, by his noise measurement, that the carrier in the pseudogap state are Cooper pairs, because they acquire angular momentum, which they are not, which they cannot have. I mean, single electrons. They cannot independently exist in a pseudogap state.
Mm-hmm. Is there a way to find out then the magnitude of this angular momentum? Is that a
electrons?
For Cooper pairs?
Yeah, we can. I mean, this is we have to. We have to calculate the energy associated with this angular momentum, and then see which will be the barrier for single electron to overcome it, and then try to measure. And this is exactly the next experimental challenge which we would like, okay, to meet. What we would like to do is to find experimentally whether monopoles do exist in this pseudogap state.
Mm-hmm.
And
what is the technique that you could use for this?
Well, another beautiful question. I know what technique can be used, but if you can suggest another one, it will be most wonderful.
Yeah.
Okay, the most straightforward way of doing this is to use the same, how does he call it, pipette-like or tip-like squid by Elie Zeldow. This is the squid, like a needle, which have resolution of a few nanometers, by which you can basically detect monopoles. And basically, what Elie Zeldow did, and this is his recent publication of his group, he detected these monopoles in the quantum Hall system. But this is not real. Those are ghost monopoles which appear when you have electric charge near topological insulator. Then they by the same Dionic consideration, so to say, they induce this image monopole there, and Elie saw them. We have real ones, and basically the same technique, and we have already discussed it a little bit with Elie. It's possible to measure them. The difficulty is like the technical one, because with his technique, he cannot go above 4 Kelvin. And on the other hand, he cannot go below, let's say, 300 millikelvin for the moment. And we have to be exactly outside this range in order to be able to measure this Dionic physics either in high TC superconductors, or we have to be in an extremely underdoped region when this TC in high TC superconductors is really low.
So the Zeldow experiment would be a very local experiment.
Yeah, exactly.
You could also think about measuring, let's say, more like a paramagnetic response to
yeah, it's possible.
Like
Absolutely, of course. And this will be a good support, and we can try to, this is what we will be trying to do now, to indeed to calculate the paramagnetic response. This will be absolutely wonderful. This will be a great support, to this concept. It will be, but it will be exactly like, you remember the situation with vortices. We can observe a lot of beautiful properties, which tells us that vortex lattice is there, but the decisive experiment was first to do this decoration, you remember, which revealed these vortices for our naked eye, or at the next step to do sort of STM experiments where we could see these vortices again by our electron microscope, equipped eye.
Yeah.
So this is exactly like that. We can think about several experiments which support this hypothesis, and also to try to carry out the experiment which will be able to detect a single monopole there.
Okay,
but
thank you.
Will be for questions. Thank you. Well.
Okay. So more questions? Actually, it was a very interesting talk today, and so I'd like to thank all the speakers. Actually, I think we had a very successful session today, even though it's almost complete online. But so we get an experience with such type of meetings, so it's fine.
Well, and I'm okay.
Yes. And also tomorrow, please note that there will be also nice talks. Tanaka from Nagoya University will give very good introduction, I guess, to Andreev reflections. So we start at 10 o'clock tomorrow. And I think all of you got the invite link for tomorrow's session. So, so it will be actually from 10 to 13 hours. Two talks by Tanaka and Suzuki. Okay.
Okay, thank you very much. And well, okay, Sasha, thank you for your help, and I'm sorry about
want to make some announcement. Yeah. Okay, please to take a seat here. Yeah.
Dear colleagues, thank you for your participation, active participation in the first day of the summer school. We have a good tradition. After the last summer school in September, it was announced a special issue of Beilstein Journal of Nanotechnology, first quartile journal, and participants submitted a lot of very good articles, and it is already published. A good journal with good impact factor and good articles. Now we will continue such tradition, and Professor Klenov just sent me email. He is the invited editor of a journal also of the first quartile, and we invite participants, listeners, our colleagues to submit new articles in this journal. The link we will send to all participants. We will send the general email for all participants with link and with invitation of Professor Klenov for publication in the journal. The deadline, I believe it is the end of March 2021, next year. That's why we have enough time to prepare and to submit. Me personally also will submit article, and I propose you to do also such, to follow our good tradition. Thank you once again, and we will meet tomorrow morning for the second day of our summer school. Thank you and have a nice evening. Goodbye.
Thanks a lot.
Goodbye.